seminars. And this third seminar will include radiation safety and also local regulation, and will also look at the cutoff level for the TB screening. So this third seminar of the regional strategy for the elimination of TB is intended to review two basic topics in the implementation of digital radiation, as well as the products that we have based on AI. In this virtual session, the idea is to present the key aspects guaranteeing radiation safety. We will also review the laws and also the evidence that we have for the proper implementation of these technologies. And in addition, we will be reviewing the various strategies that we currently have to look at the cutoff point with the idea to guarantee the efficient use of innovations in the implementation of the active search of tuberculosis. The topics to be addressed during this webinar are the following. First, we will look at radiation safety and also local legislation. We will be addressing several topics such as radiation protection, also international regulations, and also the authorization for the equipment by the regulatory authorities, as well as occupational issues. And we will also be covering, as we mentioned before, the selection of the cutoff point that will be also addressing the strategies, the tools we have, as well as any adjustment. And we will finally present country experiences. For this activity, we are offering interpretation into English and into Spanish. You can select down in the globe your language, the language of your preference. And for the agenda, as we mentioned before, we will be presenting radiation safety. This will be presented by Pablo Jimenez, who is a regional advisor in radiological health with PAHO, Washington. Next, we will see the study in radiation measurement. This will be presented by Zen King, with digital health specialist with Stop TB Partnership. And next, we will have questions and answers. The second section of our webinar will include key aspects for threshold score, as well as the tool that we have. This will be presented by Cecile Miller from WHO. Next, we will have the pragmatic approach to selection of CAD threshold reactive adjustment method, presented by Juno Ming, who is a diagnostic imaging advisor with radiologist, also with Doctor Without Borders. And finally, for the country experiences, Angelina Medina with the National TB Program in Paraguay will be conducting the presentation, and we will conclude with another session of questions and answers. Without further ado, I will give the floor to Dr. Pablo Jimenez to introduce radiation safety. Pablo, please go ahead. Welcome. Thank you very much. Good morning. I will be sharing the presentation. Good morning to all of you. First of all, I would like to thank our colleagues from the TB program to invite me to share with you some concepts on radiation safety that may be relevant for the success of implementing the programs for the control of TB in the region. I hope this is useful. Clearly, I don't know if I will be able to answer all of the questions you may have, but I can offer you an overview. As I mentioned before, I work with the Innovation Department, Access to Medicine and Health Technology, and I'm working on radiation safety. The aspects that I would like to cover this morning have to do with radiation, the biological impact, also some principles of radiation protection, also how international regulations work and how this translates into local domestic legislation, what your countries can expect from the regulatory authorities to be able to work with the equipment, and also the processes and practical processes. I will try to cover as much as I can, but I might not be able to present everything. As to the biological effect of radiation, we know that it is carcinogenic, it is bad. And if we look at this from the point of view of the cells, clearly radiation has the ability to have free radicals, but at the same time, it can break molecules, key ones such as the DNA. This is our big problem at the level of radiation, that the DNA can be ruptured, and there could be the most important problem. There could be DNA damage, and we have mechanisms that allow for repairing that mutation, and then we end up with a viable cell. This is what happens on a daily basis because we are exposed to radiation, but also the amount of radiation may lead to cell death. And instead of that cell dividing, becomes an unviable cell. We have many unviable cells, and in that case, we are going to have a noticeable problem. But it could also be a third situation, and that is that the cell cannot repair that mutation, and there could be, it could survive, but it is a mutated cell. That mutated cell in the near future could become cancer. And this is what happens even with low dose radiation. If we look at the impact, not at the cell level, but at the chromosome level, we can see here some examples of some aberrations and also some of the impacts that we may see at the level of the chromosomes, and we have several there. So mainly the problems that we have are divided into two groups, and we have some other aspects. There are some experts that may say here that are connected, may say he forgot something. This is just an overview. So there are some determinant effects. That is to say, if a person goes over a certain threshold, there will be a problem. For example, there will be a reddening of the skin, there will be mental retardation, and also slowing of the growth. And this will depend on the dose, and it has to do with, so the skin will get red up to a certain threshold, but then if I go over that threshold of radiation, the reddening will always be higher. Then we have stochastic effects. So these mutations may happen at the cell level, and they may also result in cancer. And the probability of this happening is also based on the dose. That is to say, there is no threshold, but the more tickets I get, the higher the chances that I will win the lottery. So this is similar. So what are the risks? And when we look at epidemiology, we have an extrapolation of risk, and we can assume that there is a linear relationship, there is a threshold, there is a continuation here in this line, and this is based on the dose and the probability, the likelihood of that to happen, and also the slope is 5.5% for fatal cancer for the whole population, and for the working population, and I will tell you why there is a difference among the population, whether only people that work with radiation, and this is age 18 to 65, 4.1%. So these are the probabilities for a fatal change to happen. Clearly, at the level of the tissue, not all of the tissue is the same. So this is also related to several factors. It depends on the type of cell. Therefore, here we have some tissue that is quite sensitive, and others that are less sensitive, and others that have very low sensitivity. And it depends, again, it depends whether it is the what type of tissue we're talking about, if it is nerve related or not. So this is a very complex situation to assess the risk that a person has to receive high dose or low dose radiation. We are going to talk about the dangers of radiation. This can cause problems in people, but the idea is to have strategies to protect. So here we have two goals. The first one is to prevent for the effect to happen. This is some effect that will happen. So the idea is to prevent that type, and have a dose below that. And so, and since we cannot reduce it to zero, we can reduce it to a level in which radiation is as low as possible, or levels that are acceptable. All in all, people need to be protected at all levels, either whether it is high or low radiation. Another problem with radiation is that the human body has no way to feel whether I am in a radioactive field or whether I am receiving it or not. I cannot feel it, I cannot hear it, there is no way I can sense it. So the only way to determine is to detect it. For that, we need instruments, the proper instruments for detection. And the instrument has their own limitations, but all, in order to understand the situation, we need experts, people who know what they are measuring, why they are measuring it, and also to interpret the results of that measurement. Another concept that is important to bear in mind is that we have two types of exposure. Internal exposure, when I am administered or when I am injected radioactive material. So this is internal in the organ, so there is an external source. So here we have X-ray equipment, so radiation comes after. And so in this case, there is no contaminant, but the X-ray machine produces X-rays, radiation whenever there is, it is activated, but when it stops, there is no more radiation. So these are basic concepts. Now, what are the strategies? How can we protect ourselves from that external radiation that happens whenever I am exposed? One is time. The more time I am receiving that radiation, the higher the dose, and it is also proportional. That is, if half of the time, for example, can be there, I am going to have half of the radiation exposure. So the more patients I have, the more exposure I will have as a worker. And distance, this is a great ally, in particular, when we are using mobile radiation equipment. So distance is important. Why? Because radiation will diminish with the inverse square root of the distance. So if I am 2 meters away, a fourth of that radiation, I have reduced a fourth of that radiation just because I am a meter further away. And if I get to 3 meters, there is to the ninth. The exposure is to the ninth. So I am reducing a great deal exposure to radiation by just increasing distance. And finally, shielding. Shielding is a great ally if it is possible. For example, in stationary equipment, this is very good. And shielding works by absorbing part of the radiation, and the material basically means that this is related to the density. For example, wood will not be a good protection. Concrete, bricks will be better protection. It all depends on the type of material and how I can create this shield. And whether we're talking about X-rays or photon therapy. So there could be shielding to protect ourselves, for example, when we are thinking of the lead-covered aprons or some special clothing that we can wear as well as the patient. So now we are going to see how this is regulated. We have the basic regulations on safety. These have been updated every 5, 10, 15 years. The latest one is from 2000. So how do the international regulations work? So this has to do with professional knowledge and also knowledge about the effect of radiation on people. And this is also produced by a UN committee that is called UNSER, that is the UN Scientific Committee on the Effects of Radiation. So they review scientific information to basically understand this. And from this information, together with an expert committee, with the International Committee for Radiation Protection, there are strategies, and with those two pieces of information, the intergovernmental organization, that is to say PAHO, WHO, and other organizations, or those that are interested in radiation, meet, and we produce these international regulations. And this is basically what I am discussing with you. These have been translated into the 6 languages of the UN and also to Portuguese. I'm saying this because you can find it in any language: Russian, Chinese, in Arabic. And we are currently working on the latest version. We are working with we have the IAEA, NEA, ILO, WHO, PAHO, FAO, EC, UNEP, that is the UN Environmental Program, and the organizations share this with the governments so that they can approve them. This was also taken to a resolution by our directing council with the Pan American Health Organization, and that is what the countries are asking. So they are supporting this, but those countries that using the regulation to update their own national plans, and also in the case of PAHO, they have cooperation, and here we have the member countries that are voting on these regulations. If anyone goes into the website, this is the information they are going to find. First, section 2, we have the general requirements that apply to everyone. This is basic, and you need to bear in mind that these regulations are applied to all sorts of exposures and situations, from X-ray to an astronaut that is traveling in space for a whole year. So we need to be clear where to look. Section 2, we have rules that apply to everyone. Number 3, plant exposures. We are going to plant. This is our case. We're going to buy X-ray equipment. We want to be able to use it, and we need to administer radiation. And here we have 3 positions. One has to do with the occupational exposure. As a worker, as a health worker, I am going to make a decision. I am going to do my work. I am a technician, an X-ray technician. That is occupational exposure. We can also cause exposure to the public, other people that have nothing to do with the area in which I work, or other members of the staff, officials, etc. So, and then we have the exposure of the patient, that is to say, medical exposure. I think that These are the most important topics to see if you decide to visit the web. I am going to quickly summarize this. I just referred to the various exposure situations, the planned situation, the one that we are going to see. Then we have emergency situations. Of course, we are not going to talk about that. For example, Fukushima, or if we're talking about other types of exposure, for example, in the case of other substances, and we're talking about plant. Here I'm talking about plant exposure. We have occupational, and in this case, the person who works with the X-ray equipment, that person is doing his job, so that person needs to have special protective equipment that is also regulated by means of the occupational position. So the exposure that the patient has, this is going to be a patient that will be undergoing a therapy, treatment, or will be referred to this service. And then we have the public, and the public that will be exposed to radiation, but it is not a worker or a patient. So this is, for example, a patient that was standing next to someone else that was being radiated. And clearly there are principles that are used to be able to implement the principles to guarantee radiation safety. First, we have the justification of the practices. That is, if I do something, it has to have more benefit than risk. For example, if I have X-rays for TB, at the end of the day, I want to have a net benefit even though I have a risk. So I need to compensate that risk. So a regulator will not be authorizing an X-ray to use with a newborn to see if I find something strange. There has to be a clear justification as to why I'm doing it. And then, after it is justified, I need to see how to maximize that risk. I could do things that improve my benefit or that diminish the risk. That is to say, there has to be a benefit-risk relationship. And finally, there has to be a limitation on the dosage that follows legal principles, and there are legal consequences if those limits or thresholds are exceeded. Since we're just talking about radiology today, we are going to talk about the limit of the doses for the body that is being treated. First, we have the limit, that is the occupational limit for the worker, that is over a 5-year period. This is 20 MSV, average over 5 years. And for the public, a person that is not working, the limit is 1 MSFB. So these are the limits that have been included, the thresholds that have been included in the national regulations. In the presentation, this is something that we mentioned. We are trying to have more benefits than risks. And as to medical situations, we are asking for the benefits to be higher than the risks, and also not to include radiation of the whole person. If there was, for example, something, there is another system that, or another methodology, another method I can use with the same level of benefit and lower risk, I will resort to that. But if there is no other, I will have to resort to radiation. All in all, we understand that radiation in medical situations have more benefits than risks, but as long as the regulations are complied with. Who will authorize the practice as justified? That will be the health authority, that is to say the health professional, bearing in mind certain situations. So what works in one situation is not going to work in other situations, not only within one country, from one country to the next, but also within the same country. But in this case, there is a great deal of scientific evidence that justifies the use of radiology. For example, in the case of TB suspicion, and also to bear in mind all of the health practices in this case.
Specific case of asymptomatic populations, 3158. That's a reference, and that's a number that corresponds to what we're talking about here. So, asymptomatic populations, the justification of the radiological procedures should be carried out as part of the program for detecting the disease for asymptomatic population and should be carried out with the health authority. Now, once we have that justification, then we have to optimize it. We have to do to the best possible. We have to balance benefit and risk. In the specific case of medical exposures, what we're trying to do is to manage the patient's exposure to radiation in keeping with the need for such exposure. We have to find out exactly what the right amount of radiation is to meet the purpose of the radiation and no more. Now, if I blast the patient with too much radiation beyond the protective film, now the more radiation, the more noise, and so it's not necessarily better to increase the exposure of radiation. What we need to do is optimize the level of radiation just enough to meet the medical need. Now, some aspects regarding optimization I put down here. All of the responsibility falls to someone. Someone has to be responsible. So in this case, it's the register heads, the ones with the license to handle radiation. These are the ones who are going to be responsible for all of the radiological procedures, making sure that you've optimized the protection for the patient. Now, equipment. I can use any equipment for any population? No. You have to have specific equipment for mammogram, for example. There are certain norms that have to be complied with. The requisite norms have to be applied. And if there are national requirements that have to be met, they have to be met. Now, the criteria for quality, we always want to make sure that the requirements are met. This is a mandate. You can't overlook it or flout it. Now, some operational considerations. The procedure for diagnostics, the right radiological equipment and software need to be used. You're not going to use an X-ray for a mammogram, for example, just because you have it. It's not the right machine. Now, the positioning of the patient also has to be done to minimize exposure. Expose the patient only to the degree that's necessary. Of course, you want to achieve the quality of diagnostics, so you're going to do exactly what needs to be done to achieve the medical purpose and no more. Now, optimization has to be done in a very detailed way.
A lo que nos ocupa hoy, a la sesión que nos ocupa hoy. Uno son, en el caso de que se use en pacientes pediátricos.
Now, for pediatric applications, the sensitivity radiation of a child is they're much more sensitive to exposure than an adult is.
Los individuos que sean parte de un programa de cribado de salud son individuos a priori sanos, a priori, ¿no?
So we're talking about people who are in advance of the procedure thought to be healthy. And if an embryo is going to be exposed, special pains have to be taken to avoid that. Now, calibration. The sources of radiation have to be calibrated according to international protocols. And for clinical use, well, certainly the equipment has to be maintained. Now, if your machine broke down and they changed the X-ray tube and now it's not the same as it was before, that's not how you do it. You have to recalibrate if there's going to be any maintenance done.
También se pide que haya un programa de garantía de calidad.
There needs to be a quality control program in place. The responsible parties have to have a comprehensive quality control program in place.
Lo que tiene que ver ya no con la exposición médica, sino con la exposición ocupacional, o sea, a los
Now, as far as occupational exposure, not even talking about doctors anymore, medical exposure, but the technicians, before a given practice is authorized for a new practice or modified one, the regulatory agency, as applicable, is going to review the documents submitted by the responsible parties to make sure that all of the design criteria have been met, that the potential exposure of workers be in keeping with the criteria, acceptable criteria, and so forth. On this last matter regarding modification, there has to be monitoring and records have to be kept. It's quite explicit when we're talking about occupational exposure. We're talking about a technician.
Si los límites son 20 milisieverts al año, pues tampoco queremos que esté recibiendo 19 milisieverts cada año.
You can't have someone receiving doses that exceed by far what the minimum is. So how do I know how much a worker is exposed? Now, the best way to do it is to have a personal gauge, dosimeter.
Pero obviamente lo más fácil, lo más cómodo para todo el mundo es que tenga el dosímetro personal, ese trabajador, y por tanto que tenga unas lecturas que se registren y que además el trabajador las conozca y la autoridad reguladora. Pero como digo, hay otras formas de hacerlo, pero para eso
no other way to do it other than for each worker to have their personal dosimeter. And so at least you have to have a plan and explain this to the regulatory authority for gauging the radiation exposure that workers are subject to.
Y como decía, no se trata de que reciban 20 milisieverts cada año, o 19, ¿no? Bueno, 19 estoy bien, no. Se trata de que se optimice. O sea, si un trabajador puede estar trabajando en un entorno que razonablemente
is working in an environment where that person can work reasonably without excessive exposure,
las licencias tienen que son responsables de que se optimice y de que realmente se haya hecho un
That
trabajo
degree of exposure has to be
razonable
optimized
de que los trabajadores reciban la.
and a reasonable level.
Hay una estrategia que ayuda también
There's a
a
strategy
eliminar
that
riesgos,
helps
que es
to
la
eliminate
usar lo que se
or
llama
diminish
definición delimitada de
risk.
áreas, lo que se llaman las zonas controladas y las zonas supervisadas. Como
You've
saben,
got the supervised and
normalmente
controlled
una sala
areas.
de rayos X, lo que es la zona donde está el paciente mientras
When you have
hago
an
el
X-ray
disparo, ya se
room where
considera
someone
una
is
zona
exposed
controlada, de tal
to
manera que
the
no haya nadie
X-ray
dentro de la sala mientras hago el disparo,
uh,
para que no reciban radiación. Claro, en las instalaciones móviles esto es mucho más difícil, ¿no? Pues no hay una zona delimitada, pero sí tener el concepto de que mientras hago el disparo en las zonas cercanas no haya
so
personal, ¿no?
you want to make sure actually that there is no staff, no personnel in the place where that X-ray blast is actually going to happen.
Del titular de la licencia o del empleador, en función de quién sea, si el empleador es el sistema de salud, o es una
If this is a
autoridad,
health
o es un
worker,
hospital, o simplemente
or
es
if we're talking about a
individuo
hospital, or we're
que
talking
lleva
about
la
an
licencia, su
individual,
nombre, etcétera, ¿no? Formación, otro también de los requisitos muy
training,
relevantes para la parte ocupacional.
which is
La
another
norma
very
pide
important
que se
aspect
dé
as far as
formación, información, instrucción y
occupational
capacitación
hazard.
a las personas. Es decir, no cualquiera es capaz de usar. No se trata de apretar un botón, hay que saber lo que está haciendo. Es como
It's not
cuando uno
just a
puede
matter of
programar, ¿no?
having
Yo puedo
technicians that
agarrar
can push a
le
button,
puedo
that
dar a
they
un
have to know
móvil
exactly
con
what they're
una
doing, just
dirección,
like a
tiene que ver
firearm.
la persona
You have to
tiene
know
que
how to
saber
handle
lo
it.
que está haciendo, ¿no? Qué es para qué y demás. Y eso tiene que haber un requisito de formación, instrucción y
So you have to have
capacitación.
the proper
Tiene que ser
information
acorde al equipo que
available,
estamos hablando,
and
al
the
riesgo que
proper
estamos
training
trabajando. No es lo
instruction
mismo
has to be
un trabajador
given
que va a
to
trabajar, yo qué
the
sé,
workers according to
haciendo
the position
radioterapia
that
en un
they
acelerador
hold.
lineal, que necesita una capacitación más extensa que una persona que va a hacer unos disparos con un equipo portátil, ¿no? Pero
Someone
tiene
who's
que
going to be
haber
working
un
with an
nivel de
X-ray
instrucción
machine
y
has to
capacitación
receive a more
similar.
thorough training than someone who's going to be
El
using
regulador
a handheld
va a
radiation
pedir,
device with a
lo que pide la norma
lower
es que,
dose
uno,
exposure.
que la persona que va a usar el equipo
The person who's
esté
going to use
especializado en la
the
esfera pertinente. Es decir,
equipment.
si es de radiología, que sea un técnico o tecnólogo en radiología, no que sea un
It should
técnico o
be
tecnólogo de medicina
a
nuclear, por
radiologist,
ejemplo, ¿no? Y va
someone
a pedir
trained in
cuáles son, que se
radiology.
cumplan los requisitos que ellos han establecido de capacitación y competencia en protección
And they have to
radiológica.
be in compliance
Normalmente,
with the requirements, meet
depende
the
del país,
requirements
¿no?
that are established.
Normalmente se suelen pedir cursos o
The
cursillos
regulatory
de
authority
unas
is going to make
10,
sure
20
that
o 40 horas,
the
depende
proper
de las
authorization
especialidades. Y eso la autoridad reguladora pide que las
has
personas que
been
tengan esa
issued for
capacitación
any
o bien la han recibido durante su formación
workers who are going to be
académica, porque
exposed
a lo
to
mejor yo que soy
radiation, medical
tecnólogo en
radiation,
radiología, mi formación incluye ya una asignatura
and
y
that
entonces la reguladora dice, vale, con esto me sirve y no hace
the
falta más. O no, si dice,
responsibility
no tengo
be
claro si
taken on by
quiero que hagas
those
un
people
curso
to
de
be
10 horas
holding
o de
those
20
positions.
horas
The
de estas
right to
temáticas
course, a
para
10,
cumplir la
20-hour
carrera.
course
Pero
on
eso
the
lo
subject
ejecute
matter
el regulador.
should be given.
Y que
This is
los
something
nombres
that
de
the
esas
regulator is
personas,
going to
los
ask
nombres que van
for.
a usar
The
el
names of
arma,
the people who are going to be
tenemos la
using
lista. Es decir,
that
quién va a usar el
device.
equipo.
You have to have a
El
list of
equipo lo
who
voy a
is going to
autorizar que
be
se use, pero
using
quién
the
va a estar haciendo el disparo,
devices.
¿no? Esto es un poco lo mismo. Tienen que estar esos nombres en una lista actualizada.
You have to
Y
have an
eso
updated
más o menos
list.
es lo que dicen las normas internacionales. Dicen
This is
muchas
what the
cosas. Yo
international
creo que les oriento
rules,
un poco por dónde
standards
va
say.
los tiros. El problema de la norma es que dice qué es lo que hay que hacer, pero no dice
The
cómo se hace.
standards say what
¿Cómo se
needs to be
hace?
done, but
Y
not
para eso
how it
sacamos más
is
recientemente
done.
esta guía que está aquí, Protección y
Now we
Seguridad
have
Radiológica en los usos
these
médicos de la radiación. En este caso
guidelines
solamente
for how things
sea por
are
OPS, por
done here.
OIA, por la
This in
parte
reference to the
por,
mobile
por la
uh,
OIT, por la parte ocupacional, por OPS y por OMS.
X-ray
Y de
device.
esta guía, que también está disponible en inglés y en
This
español, creo que también
handbook,
en
or
otros
these
idiomas, no
guidelines are
recuerdo, pero en
available in
inglés supongo que
Spanish and
seguramente
English,
lo pueden encontrar. Pueden ir, por ejemplo,
and
a
I'm
la parte
certain you
específica
can
de
find it.
radiografía móvil. Básicamente lo que se dice es
Now, as
que,
far as
ya que es una
mobile
guía, no son
X-ray,
requisitos, son guías,
these aren't
se
requirements, these
usen,
are
los operadores deberían
guidelines.
usar el delantal diplomado sin mantener la distancia posible entre ellos y los
You
pacientes para
stay
evitar
as
esa
far back
radiación
as
dispersa.
is necessary. You have
También
a
no se olviden de
lead
que tiene que haber supervisión visual y auditiva con el
apron.
paciente en caso necesario. Que los otros trabajadores que no
The other
son parte
workers
del
who
proceso
aren't a
no
part
se
of
consideran
the
exposiciones
procedure,
ocupacionales. Si es posible, la forma de mantener esto es
that would
que
not
al
be
menos
normally
intente
subject to occupational
tener una distancia de 3
exposure.
metros del paciente.
they should stand back at least 3 meters. We're talking about dispersed radiation. No worker should ever be exposed to direct radiation.
Que, por supuesto, antes de dar el disparo, que se haga, en el caso de radiografía móvil, que se haga un aviso verbal, al menos, voy a disparar.
Shooting the radiation.
Todo el mundo sepa que va a haber el disparo, ¿no?
Everyone needs to be alerted that it is about to happen, so they can take the necessary precautions.
O personas que pueda haber cercanas dentro del paciente que se está siendo explorado. Para los equipos fijos,
Now, for
normalmente
the
estos equipos lo más fácil
teams,
de protección es las barreras, es decir, usar barreras de blindaje.
There should be shields, barriers, brick, or any type of material that would protect them from radiation. This document was prepared a couple of years ago. It's available in Spanish and English on PAHO's webpage. This is shielding against the minimum size necessary for proper shielding against X-rays. We're talking about 16 square meters. A methodology is established for the calculation to determine exposure based on the size of the room, and if there's any sensitive material. This is based on estimates taken from a workload of 3,000 patients a year. And so this handbook is quite useful, and you should take a look at it. Lastly, we have the issue of authorizations. Everything we've been talking about, basically, what do the standards say? These are international standards that are applicable to all practices, unless you are excluding, unless there's some aspect that's that's exempt, including requirements for reporting or notification. We're talking about such a low dose radiation from an X-ray, such a low intensity that it doesn't fall within it doesn't trigger the regulatory authorities' oversight. But that's not our case. In our case, we have certain requirements that have to be met regarding notification. And there's always going to be a safety assessment carried out. Now, the standard. Not everything applies equally and for all situations and all levels of intensity. It's going to be gradual or graduated. If we apply this gradual approach in this graded approach for authorization, now exemption.
Los equipos de rayos X no hay ningún país que los va a dar por exentos, o sea que van a tener que entrar al control regulador. Notificación es suficiente, bien.
You have to have sufficient notification.
En estos dos casos son autorizaciones. Lo más normal es que equipos de rayos X entren o bien en un registro o en una licencia.
Machines need to be registered.
No sea necesaria una licencia para un equipo de rayos X, porque
you don't always have to have a license for all types of equipment. Depends on the level of risk. Now, what is a license? It's a legal document that is issued by a regulatory authority, whereby authorization for carrying out certain activities related to the installation of the equipment or its operation. Such a license has to be issued. And of course, you have someone who is the person responsible for safety and the possible risk that the use of this equipment entails. Now, in my personal opinion, We're talking about portable X-ray machines. This is a form of authorization for practice in the case of low or moderate levels of risk, based on which the responsible party and for which the responsible party has undertaken the necessary assessments, security evaluations of the installations and of the equipment that is then submitted to the regulatory authority. The practice or the use then of that equipment is authorized by that regulatory authority with certain conditions or constraints, whatever conditions or constraints may apply according to that regulatory authority. You have to be clear about the equipment, who made it, you aware of the security concerns and requirements. There might be a certain degree of risk. The evaluation requirements for security and the constraints or conditions that apply to a given practice can be less rigorous for the registry than for the granting of the license, that is, for this device to be registered, than for the actual granting of the license. So that concludes my presentation. I hope I have illustrated some of the concerns. The important thing to take away from this is there has to be some type of authorization granted for the equipment and those who are going to be handling radiology machines. So each one of the countries are going to have to, people working in radiology are going to have to be apprised and knowledgeable about the local or national requirements, regulatory authority, authorization requirements in each country. Thank you, Pablo, for your very detailed presentation. Now, after the next presentation, we will have an opportunity for Q&A in which you will be able to ask your questions. You can type them into the Q&A function on Zoom. Now I'm going to give the floor to the digital health specialist of the partnership, who is going to talk about the study for radiation, study on radiation measurements.
Thank you, everyone. I hope you can hear me and see the screen. Apologies for not being able to present in Spanish, but I hope the translator will be doing a good job. So my name is Jujensi. I'm a digital health specialist from the Stop TB Partnership. Today I'll be presenting on the results of our assessment of scatter and leakage radiation from those portable digital X-ray system. It's a collaboration between the Stop TB and the MSF. So next slides. So given I think our colleague also mentioned that given the recent updates of the IAEA WHO minimum specification, there's a new type of digital X-ray that are becoming more and more available on the market, that is portable or ultra portable X-ray. One of the couple of hallmark of these type of X-ray is that the X-ray generator, the voltage is usually much lower than the stationary X-ray, ranging from 50 kV to normally not less than 90 kV. That's what's the WHO IAEA minimum specification, although preferably to go up to 110 kV. In the X-ray generator's current time range is significantly less than the stationary X-ray, from 0.5 to 2.5 MES. recommended to go to 0.3 MES up to 100 MES. And the DAP display is recommended, but it's not always available. This type of ultra portable X-ray, because of the innovation in the image synthesis, it makes the dosage much more efficient in converting the imaging. So the detector panel is much more sensitive. That's why the output powers and voltage and whatnot are much less than the traditional fixed X-ray you see in our hospital or the mobile X-ray that you see in the hospitals. I'll skip what X-ray radiation is because the previous speaker has covered that very well. And okay, there are several types of radiation concerning the radiographer, the operator, the TB screening staff, and the general population. There are obviously the principal beam, primary beam that is given to the patient, and patient will absorb most of the radiation, but that's not what we're looking at this time. We're looking at what are the radiation exposed to the operator as well as to the general population. And this includes mainly two types, which is leakage dose that you see on the graph, and the scattered dose. So these are the radiation not absorbed by the patient, but bounced back and scattered in scatter format. These two types of radiation pose potential occupation hazard to the radiographer, although they're less intense, but because the screening staff are exposed every time when they take an exposure. So the question we have seen from country and program is then how much radiation, accumulated radiation there is for a radiographer, how much risk there is, and how to keep them safe. So this is the main main purpose of the study. Within this, we applied some of the international radiation safety standard, the ALARA principle as low as reasonably achievable. We're also using two main radiation dose limit. The the IAEA recommendation for staff operators as a yearly maximum radiation dose limit is 20 millisievert per year. That is 20 times of the maximum recommended dose to general population. For the simplicity and being more conservative, because we want to apply to general population, general public, and potentially plants and plantations in the public. So we use the more conservative limit, the lower limit, 1 millisievert per year when we perform the calculation. So just to reinforce our aim of the study, what we'll be presenting today will be focusing on we'll be performing a standardized evaluation, and it's independent from any vendor on the scattered and leakage radiation dose by ultraportable X-ray, and we use that as a basis for the radiation safety guidance for TB screening. These are the 4 types of ultraportable X-ray included in the study. The reason for the inclusion is those are the main 4 types that were available. I'm willing to send the devices to our testing lab in the Netherlands, and we're willing to publish their data regardless of the results. So this includes min X-ray, Delft imaging, Fujifilm, and Sinopharm SIUI. You can see the KV range indeed are more or less within the WHO IAEA recommendation. The Sinopharm is slightly higher, can go up to 100 kV. And it's also the most powerful one in terms of MES as well. The Fujifilm XR device is the least powerful one. It can only go up to 2.5 MES. These range are relevant because we're also taking those range, the commonly acceptable range, in our calculation. We also took the manufacturer recommended setting when we set up the experiment. So this is how we set up the experiment room. We use a Anderson Phantom for the study. No human subject involved. This also we do that also to ensure reproducibility of our study, to minimize the minimum variation in experimental design. Again, so these are the 4 types of radiation we're measuring, including the primary radiation, that's the primary beam, then the leakage radiation, and scatter radiation, as well as the entrance skin dose that's been by the patient. So here is the results starting from here. In terms of scatter radiation, this is the scattered radiation as per the 4 X-ray system per exam, and at each angle of the X-ray generator. So the left graph shows the SSD of 1.8 meter, and the later one shows the SSD. So as you get closer to the source, obviously the scatter radiations get larger. These 2 SSD were chosen because of the manufacturer recommendation, but we're using 90 kV and 2.5 MES for all 4 systems. There's some slight variation of the 4 ultraportable X-ray system, but more or less you can observe that there is a pattern. It looks like in the shape of the bunny, the scatter radiation. More or less, the scatter radiation makes sense. It's the lowest directly behind the patient, representing by here, and it's the highest directly behind, if we're taking a PA position, directly behind the patient, 180 degrees, or at the 90 or 270 degrees point. This it also looks like a bunny, but this measures the distance, safety distance. The line, the red line is a dotted or faded line, represent the 1 millisievert. Remember, that's the international recommended standard. This is the isodose line, correspond to the lowest public recommended yearly dose. And the distance represent how safe, how far the radiographer should stand from the patient and from the X-ray generator in order to be safe if they are performing. So the line represents, the solid line represents if they perform 200 X-ray per day and 5 days a week and 52 weeks a year. So obviously that's a very high throughput. And it makes sense that the radiographer should stand further away from the X-ray tube, as was the patient, as far as 9 meters from the patient, if they perform 200 X-ray per day, and then working full time. But there are also some other position where the scatter radiation would be lower, for example, directly on the left and right of the patient instead of directly behind. So this is just accounting for the scatter radiation. We also, obviously, there's also leakage radiation that is leaking from the tube, as the name suggests. So the radiographer actually is subject to the sum of these 2 types of radiation. Now, what we did is we calculated the total dose at the 180 position, the highest scatter radiation position, plus the leakage dose in that position. Then we presented a couple of scenarios. We set the KV at 90. Again, we selected 3 types of MES, 1, 2.5, and 10 MES. And the SSD we keep at 1 meter to 1.8 meter. The tube distance to the tube is either 1 meter or 2. And wearing lead apron with a thyroid shielding, a thyroid collar, or without. So here is a result. This is the main results slides. So remember SSD on the left, it shows SSD 1.8. On the right, it shows SSD 1 meter. The rest are the same. So SSD, again, this is when some X-ray manufacturer recommend a SSD of 1.5. So we chose between 1.8 and 1 meter. So so looking at the slides, for example, if we're using 1 microsievert a day and we're taking 90 kV, right? And the dotted line, the solid line is represent the total number of exam per day performed to be safe, to be under the 1 millisievert per year without wearing a lead apron. And the radiographer will stand 1 meter away from the X-ray tube. That means under this scenario, it's safe to perform up to 200 exams per day without wearing lead apron. But if you alter, as our previous speaker mentioned, there are ways to keep people safe. One way is by providing a shielding, wearing a 0.25 mm lead apron. Then the number of maximum exam per day to be safe increased to 1,032. But 1 microsievert is very, very low. And it's pretty standard to use 2.5 MES. So in this scenario, usually standing 1 meter away, if possible, then it's safe to perform with a lead apron. It's safe to perform 175 exam per day. And the results showing here represent a different scenario that is needed for the radiographer to perform. Now, so in conclusion, there are several, because the setting up scenario can be very different, and I'll share the slides. So what this study was trying to show is, yes, there are risks that are exposed to the radiographer and to the patient, but there are also means to reduce the risk. And here is specifically present in numbers, what is then a safety number of maximum number exam performed per day before some alternative measures should be in place. Already with the scenario, there are things you can change, including increase the distance to the X-ray tube. So some of the ultraportable X-ray has increasingly improved by giving us the remote control. This allows, instead of using a wired switch, so the radiographer can stand further away, 2 meters or even further away from the X-ray tube when taking exposure. Now, there are also other ways to reduce the risk if the maximum number exam is reached. One is obviously time. The radiographer can work in shift. It's recommended to wear a dosimeters that record the accumulated dose to the radiographer. So if the maximum is reached, then working in shift is an option. So another is distance. So as I mentioned, using a longer exposure cord or remote control. Site selections, site design, for example, including where using natural shade to position the patient so that they don't face directly, or the general publics, there are no general publics directly in the radiation zone, as you see in the bunny shape. Shielding, lead apron plus thyroid color provides significant protections. There are also other type of more extensive shielding, like a mobile lead barrier that will also help provide additional shielding. So with that, I want to acknowledge the team that is working on this project, everyone listed here from the MSF team. And also I want to appreciate the vendor who provided the equipment for the testing. I also want to acknowledge that they have no influence in whatever way in the study design or the results. Thank you.
Thank you, Giselle, for your excellent presentation. A continuación, vamos a dar paso a la sesión
Next,
de
we'll
preguntas y
have
respuestas que corresponden
questions
con
and answers
las dos presentaciones anteriores.
about the
Le
previous
paso
two
la palabra a nuestra
presentations. I
colega
give the
Becky
floor to
Marcelino
our
para que nos guíe
colleague
esta
Becky
sesión.
Marcelino
Adelante, Becky.
to
Gracias, Ernesto.
guide this
Muchísimas
session.
gracias,
I
Pablo
thank
Jiménez,
you. I
Giselle,
thank Pablo
Giselle,
Jimenez. I
for the
also thank
presentation.
Zizen.
Vamos a leer las preguntas.
John, we are
Varias
going to read the
preguntas de
questions. We
nuestros
have several
participantes. La
questions
primera es de
by
Ivonne
from
Montiel,
our
que nos
participants. The
pregunta
first one is
cuál es la
by
distancia
Montiel, who
mínima
is
que
asking what
debe
is the
haber entre el
minimum
equipo
distance between the X-ray
y las personas
equipment and
sin que
the
esto implique un
individuals
riesgo
without
elevado
this
para las
implying a
personas.
high
No sé
risk
si
for
Pablo
individuals. I don't know
quisiera
whether Pablo would like to
responder.
address this.
Primero Pablo, luego Giselle.
Pablo and then
Bueno,
Zizen.
la pregunta es que cuál es la distancia
So what
mínima,
is the
¿no?
distance, the minimum
No hay una
distance?
distancia
There
mínima
is no minimum
para
distance
hacer la exploración. De hecho,
for the screening.
algún tipo de exploración
As
puede
a matter of
hacerse
fact,
teniendo que
for
estar
some
relativamente
screening,
muy cerca
it
del
can be
paciente.
done,
Lo
but
que
the
hay
person needs
es
to be really
que,
close to the
primero,
patient.
respetar los
So
límites de dosis
first, there is a
todos los
need to
ocupacionales que
respect
pueda tener,
the occupational
que son, como
threshold,
se ha dicho, 20
and
milisievert
as
por
we
año a
mentioned,
16 minutos.
20
Una vez respetados los
millisieverts
límites,
a
lo que hay que
year.
hacer
And
siempre es
then what
optimizar lo
we
máximo
always
posible. Es
need to
decir,
do is
hacer
to
todo lo
optimize,
posible
that is to
para
say,
que
to
el
do
usuario no venga,
everything
reciba
they can
cero o
so
uno
that they don't
o
receive
todo o nada positivo.
20, but less
Entonces,
than that.
lo importante
Once again,
es, en
it
este
is
caso,
important in
usar la
this case
distancia
to
mayor que pueda
use
del
the
paciente en este
highest
tipo de rayos X,
distance
por lo que acaba también de comentar la
from the
colega
patient and
Marcelino
also
de fuera.
from
Es
the
decir,
X-ray equipment.
cuanto más lejos esté, mejor.
The further away, the better.
Pero no hay una distancia mínima
But
ni
there
nada.
is no
Puedo estar a 3
minimum or
metros, puedo
maximum
estar,
distance.
puedo
If he
estar a
can, the
1 a 2
person can
metros,
be 3 meters
pero si
away, better
necesariamente
than
va a haber
2.
un tipo de
But
exploración,
for
tengo que estar
some
muy
screening,
cerca del
I need
paciente,
to be
eso sobre todo en
really
casos de
close to the
exploraciones de rayos X, pero y ese tipo
patient.
de
I
exploración de
can't
rayos
think
X
of
donde no
other
tienes que estar muy
situations, but
cerca
in
del
some
paciente,
cases, the
pues hay que
specialist
estar. En
is
ese
really
caso,
close to the patient.
no te queda otra que estar, eso sí,
That's
con
all you have to
ozono,
do.
etcétera, etcétera.
So
Se trata, por tanto, de usar las técnicas para
then
minimizar
you need
al
to use the
máximo la radiación que va a
techniques to
recibir el paciente
minimize the
disponible
amount of
de rayos.
radiation to be received. I don't know if I am answering your question.
Giselle, sí. Gracias, Pablo.
Zizen?
Giselle, sí.
Thank you, Pablo. Zizen?
Sorry, I was on mute. I think the slide that I was showing before illustrate and I agree with Paulo that there's no standard for one minimum distance. There's required distance that in order for the column mission to cover the entire long field, and depends on where anatomical parts that you are taking exposure. So this SSD is sometimes depends on what the X-ray setup and what parts you're taking. Then there's also a distance. We need to also be clear what distance we're talking about. There's also a distance that's between the X-ray and the operator. So as I said before, here we have demonstrated that this distance, safety distance, depend on a lot of parameters. Depend on the SSD, depend on the MES, depend on if the radiographer is wearing lead apron or not. So this slide show what's the safety distance, but obviously if the radiographer can stand as far as possible but still operate, then the longer the better. Over.
Thank you. Continuamos entonces
We
con
then
la pregunta
continue
de
with the
Iván
question
Cardosa,
by Ivan
que
Cardosa.
nos pregunta cuáles serían los criterios
That is,
para
what would
realizar
be
rayos
the
X con equipos
criteria
portátiles. Creo que se
to
ha
have
respondido en la
X-rays with
presentación.
mobile equipment?
Y
I
resumen,
think
los
that this
criterios
has been
para
discussed. What
realizar
are the
la rayos
criteria
X con equipos
to
portátiles.
do X-rays with mobile equipment? The criteria, and just to summarize, first, the equipment has to be manufactured with safety standards. They need to comply with the electrotechnic organizations, international electrotechnics regulations, because first we're going to have the electrical safety, the mechanical safety of the equipment, and also what is important, the radiation safety. The equipment has to comply with all of this. And also, there is a need to comply with the national regulatory authorities to allow for the use. For example, if there is a registration or a license, usually there is a need for a registration. What are the criteria? The person using the equipment needs to be properly trained. They need to be an X-ray technician or whatever the name is in each country, and they need to have the knowledge about radiation safety and minimum training. It doesn't have to be that broad. And also there needs to be a safety study for the equipment. For example, what our colleague presented us, for example, these equipment include a certain measurement. These are the typical radiation measurements, and with that information and the description of the equipment, usually the regulator has the information, has the technician, the safety study, and then it is determined whether it is reasonable or not, and whether the minimum regulations are being met. This is a summary, but there are several elements that come into play here. Thank you, Pablo. Suzanne, do you have anything to add?
Pablo is very comprehensive in his answer, and the only thing I would add is that there are the minimum technical specification WHO IEA has put out, and that outlines in detail hundreds of criteria when selecting mobile X-ray. So I'll recommend you refer to this document. Over.
Thank you. Gracias. Sí. La siguiente pregunta es la de Alberto Mendoza, que nos pregunta.
Now we have Alberto Mendoza's question. Shouldn't there, if there is, how about active X-ray detection in kids, for example, that are in foster homes? What is the type of care we should have for children? Once again, I have not addressed pediatric specifications, but to begin with, there is a higher risk for children to have adverse effects throughout their life. Therefore, there must be higher care with them. First of all, justification, whether the procedure is justified or not, if the risk is higher, if there is a lower benefit. Now, if the benefit, the expected benefit is higher, then it should be carried out. Now, precautions, very basic. For example, the nets that are used to prevent scattering should not be used because this increases the radiation, and the kid does not have a mass, a body mass to lead to scattering. So there is no net that should be used with them to prevent scattering. And this is basic, but everything that has to do with the proper selection of the radiation, so the minimum, but it is not too much. It is very easy to increase the milliamperes per second, and that will also reduce the radiation. And clearly, other operational aspects, sometimes kids need some sort of supervision to be in the right position. They need to be in the right position. There are some systems that are used for positioning, and sometimes it is necessary for someone to hold that kid. And that person should be a family member, but not the worker. A family member, the father, the mother, a sister, or brother, because in that case, nothing happens if the relative receives a little bit of radiation once in life. If it is every day, well, then we need to rethink it. But these are just some general recommendations. Thank you, Suzanne.
Yeah, that's very comprehensive as well. Only just to add that I think for children and pregnant women, they're more at risk of radiation. The adverse effect of radiation is more severe, so that shifted the risk-benefit analysis. And I think Cecily also mentioned here from the WHO in the chat that in general, WHO does not recommend the using X-ray for systematic screening, TB screening in children unless there are prior risk factor, either their contact or PL-HIV. Over.
Ernesto.
Sí. Bueno, gracias a los dos
I
expositores.
thank you, both presenters.
Se respondieron las preguntas que
The
estaban
questions have been answered,
en el cuestionario.
the questions that we had in the questionnaire. So now we are going to continue with the session. We invite you to stay with us up to the end. And now we are going to move on to Cecile's presentation from WHO, who will be addressing the key aspects for selecting the threshold score and also the tool that there is for that end. Cecile, please go ahead.
Okay. Hola a todos, gracias otra vez por invitarme.
Hello, everyone. Thank you very
presentar.
much for this invitation to present.
I will speak in English to give my presentation. I think everyone will be happier. But thank you very much again for having me at your session. I'm going to present now on behalf of colleagues in the special program for tropical disease research from WHO, as they developed this CAD calibration toolkit that I will be sharing with you today. We worked closely with them to do so. I will present today on behalf of Dr. Corinne Merle from the TDR program. Can you see my slides okay? Is the presentation mode?
Go ahead, Cecily. Yes.
Okay, great. So this session is, we'll present the TDR toolkit for CAD calibration. So this is an operational research approach that you can use to select the calibration, to select the threshold score for your CAD product. So as we all know, as we presented a few weeks ago, since 2021, we now have a recommendation that CAD can be used alongside chest X-ray for screening and triage in those individuals over age 15 and over. However, we need to keep in mind with CAD that the performance of CAD is not the same across all populations and all settings when set at the same CAD threshold. The way that it acts as a screening tool can be influenced by specific factors in the population that include the severity of TB disease and the prevalence of TB in that population, the presentation of TB in the individuals who are being screened, as well as those that have other comorbidities, and the proportion of lung disease in general, besides TB, that you see in the population being screened. So you have to keep in mind what spectrum of lung presentations are you going to see in the population that you're screening. And this will help influence, along with other factors, where you should be setting your threshold for determining whether an image is determined to be abnormal or normal. So when we talk about calibration, we're talking about determining an appropriate threshold above which a chest X-ray is considered abnormal or a positive screen, and that person will go on for further evaluation. Now we have a trade-off when we set our calibration between sensitivity and specificity. So the lower we go with our threshold, you can see this line here from 0 to 100. It can sometimes be from 0 to 1, but the principle is the same. The farther you go towards 0, towards the left, you are increasing your sensitivity because the more people you will screen as abnormal, the more prevalent cases of TB you will detect. But you'll also incur much higher costs in terms of testing, follow-on diagnostic testing, because you'll have more false positive results as well. The further to the right on this you put your score, the higher your specificity, meaning the less extra costs you will incur for follow-on diagnostic testing, but the less prevalent TB cases you will detect in your screening strategy. So in order to determine where you set this threshold, you need to understand some questions about your screening project, including what are your goals for this screening or for this triage? Are you trying to maximize case detection, or are you trying to most efficiently determine which people should go on for diagnostic testing? And what are acceptable costs for you? How much can you spend on diagnostic testing in addition to screening? So the CAD calibration toolkit provides some support to help implementers conduct an operational research study to calibrate CAD for their setting. The program is also designed to help understand the implications of different threshold scores that you might choose in a specific context, including what the specific accuracy, sensitivity, and specificity of any particular threshold score that you might choose would be, and what the cost implications of any choice would be as well. It also provides an operational research protocol that you can follow to help implement a calibration study. And there's also an associated web tool to help analyze the data that you would gather through this operational research study. And there are some analysis aids with the toolkit to help you make sense of your results after you've done such a study. So the calibration toolkit has three main parts. The first part is a background document that describes what a calibration study is, how you would conduct one, different approaches for the methods you could take. Part B is a generic study protocol. Part C is a user guide to support the analysis and interpretation of the data, as I mentioned. And there's also a web tool, which we'll get to in a minute. So the overall setup of a calibration study is pretty similar to any diagnostic accuracy study. You will have a selection of patients, and for those patients, you will have their CAD score and the ultimate TB result. So the patients will be divided according to their CAD score into abnormal or normal, depending on what threshold is used for any particular analysis. And you will also have the results of bacteriological examination for all these patients. So you'll know whether they are truly a TB patient or a non-TB patient. And then according to that, they are categorized as a true positive would be a patient with TB whose CAD score was above a certain threshold, not TB, determined to be not TB, but would be a false positive if they still have an abnormal score. And patients that don't have TB but are considered normal would be a true negative, and then a TB patient but has a normal score would be a false negative. So to conduct a CAD calibration study, there's actually not that much data that you need for any particular person. As I mentioned, for each study participant, you would need some key clinical and demographic patient variables. You would need to have, this usually includes gender, age, and perhaps key comorbidities that you might be wanting to look into. This could include HIV in certain settings. It could be patients that have had a previous history of TB, or it could be patients with diabetes. Again, it's dependent on if there are key comorbidities that you want to investigate. But the most important items are that you need to have a chest X-ray and have a CAD score for each person, and then you need to know their TB status, whether they are diagnosed with TB or not. And the data for these types of studies can be collected in two ways. You can collect them prospectively, or you can do a case control type study and use retrospective data. So you can use pre-existing data if there already are data, for example, that were done from a prevalence survey, or any previous screening efforts that have been done in the population that you plan to screen. If there are existing chest X-ray images that are available to be used, for example, from previous studies, and if you have the TB data on everybody who was screened, you can use this data. So there are a few different ways that you can put this together. You can do a retrospective case control study if you have existing data that you can sample. This can be a very efficient way to conduct such a study. This would be, for example, if you have prevalence survey data available, This could be a very easy way to implement this type of study. You can do a combined retrospective and prospective case control study if you have some data available, but there are other types of data that you don't have. For example, if you have data from TB patients, but you don't have data from people who are not ultimately diagnosed with TB, you can use the data you have and then prospectively gather more data. If you don't have any data on hand, you can do this prospectively and gather the data prospectively as you implement. However, this can have a higher implications and costs in terms of the sample sizes required. So speaking of, we can look at the sample sizes required here. So if you can use a case control design for this type of study, so you sample patients who were diagnosed with TB and patients who were not diagnosed with TB, this would be the most efficient approach for this type of study. If we look at the graph here, and if we aim for the precision around an estimated sensitivity of about 90%, you can see that our sample size would be about 138 patients with TB and then about 138 patients who are ultimately not diagnosed with TB. So your total would be about 276. If you end up having to do a prospective study where you cannot sample TB patients and non-TB patients separately, and you have to just sample from one population going forward, then the sample size that you would require depends on the prevalence of TB in that population, because you're probably going to get plenty of patients who don't ultimately end up having TB, and it'll be a little bit harder to find sufficient number of patients who do have TB. So if we use the same principle and we look for the precision around a study of about 90% sensitivity, again, we would need 138 TB patients. And if we assume a 2% prevalence in the population that you're screening, you would need to enroll overall about 6,900 patients to find sufficient TB and non-TB to conduct the study. So within this study, you can also do sub-analyses. So I was mentioning this earlier. You can select some characteristics for which you can do subgroup analyses to also see how the CAD threshold might operate separately in patients with certain characteristics or risk factors. So for example, you can look separately at different age cohorts, maybe under 55 years versus over 55 years. You can, of course, look separately at patients with different HIV status, or you can look separately at patients who've had previous TB. These are all factors that we know affect how a CAD program operates. So for these different types of subpatients, you might want to think a little bit differently about the score that you're using. So this is a brief overview of the tools that are provided alongside the calibration study. We have a data collection template on the left. So this can be used to gather the data from the sample of patients or participants that are being enrolled. There's a CSV data entry file, so you can easily enter the data that you have into this and then upload it into the online data analysis tool, which you see on the right here. So this tool allows you to upload the data when it's entered into this CSV format, and then it will take the data and it will analyze and calculate the sensitivity and specificity of this particular CAD product across a range of different possible threshold values. And it calculates a number of implications of each of those scores, which might include the number of TB patients that are found, the number of false positive diagnoses, and some cost implications. So it also creates an ROC curve, which you see here, for the product. So this shows the curve along all possible points of all possible thresholds that you could use for the CAD product. So it shows for any possible threshold what the sensitivity and specificity of that threshold would be. And you can see sort of how the CAD product operates as a whole. And then again, I mentioned earlier, this is the type of data that it produces as well. So it shows you on the left, all the way on the left is the potential cutoff that you're seeing. So this particular table starts at a threshold of 10 and it goes all the way up to 20. So there would be many more rows for any other possible threshold for this product. And it shows across this whole population, you can see, for example, for a threshold of 10, what the sensitivity is 99.5%, and the specificity is 15.9. So this is a very sensitive but not very specific at all particular threshold. It shows you how many cases you might miss and the percentage of overall cases that you're missing. So here it's 0.5% cases missed. The cost per case, which we see is quite high using the very high threshold, and the extra cost that you might incur due to over-diagnostic testing, essentially. So here is where you can access this toolkit. You can go to the website or use the QR code. I would encourage you to reach out to the colleagues at the TDR program or us or the colleagues there in the PAHO regional office if you'd like to utilize this toolkit and conduct a CAD study, so you can be provided with some assistance and some guidance. And I just want to again say that I want to thank the colleagues in TDR, Corinne Burl and Vanessa Veronese, for putting this toolkit together. And I'm happy to answer any questions. Thank you.
Thank you, Cecil. A continuación vamos a presentar a Juno Min, quien es asesor de diagnóstico.
Now, Juno Ming, who is
de Médicos Sin Fronteras,
from Doctors Without Borders, and she is going to give us a practical focus for the selection of CAD thresholds.
Adelante, Juno.
Juno.
Hello, thank you for the introduction. Like Cecily, I'll be giving this presentation in English. Let me just start by sharing my screen. So my name is Juno Min. I'm a diagnostic imaging advisor at Doctors Without Borders, and I'm a radiologist by background. And today I'll be talking about a pragmatic approach to selection of CAD threshold, the reactive adjustment method. So just a brief outline of what I'll be talking about. First, a bit of background about threshold calibration. I'll describe our reactive adjustment technique, which involves two steps. There's the initial threshold selection, and then there's threshold adjustment. And then I'll show some of our country experiences in MSF in the Philippines and Tajikistan to show you how we've used these techniques or this protocol in action, and then conclude with a brief summary. So I won't talk too much about CAD threshold selection. Cecily did a nice job of summarizing the main points. The CAD performance does depend quite a bit on which threshold is selected. And as Cecily mentioned, there is a trade-off between sensitivity and specificity when choosing your threshold. It does need to be calibrated to local conditions. Cecily mentioned some of the factors that can affect the CAD score, including population characteristics, the CAD product itself, and even the software version can affect the CAD scores, and the X-ray equipment. So because of these factors, the threshold does need to be selected specifically for the local context. So there are different strategies for CAD threshold selection. Some of these are described in guidance from StopTB. Zhizhen has written a comprehensive guide to implementation of CAD and ultraportable X-ray, which describes several of these strategies. There's comprehensive operational research. So this is what Cecily was talking about, this calibration toolkit from WHO, TDR. And it's the most scientifically rigorous method to select your threshold. However, it does require significant time, resources, and research capacity, which may not be feasible for some projects. There's another option described, iterative operating point calibration, ITSC, which we won't be discussing today, but just so you're aware that there are other options. And today I'll be focusing on reactive adjustment. This involves selection of an initial threshold and adjustment of the threshold based on periodic evaluation of data. It's an adaptive response to certain data indicators and allows for rapid and flexible adjustment. So I will talk about our the technique that we used, our approach to threshold calibration based on reactive adjustment. This is a method that we developed to use in our projects in MSF. So basically it involves two steps as I described before. There's the initial threshold selection, basically an estimation of an appropriate threshold to start with, and then the threshold adjustment. As mentioned, we evaluate certain indicators at periodic intervals, and based on those indicators, we determine if the threshold needs to be adjusted. One of the benefits of this approach is it does not require confirmatory test results prior to the start of activity. In the toolkit, as Cecily mentioned, you may be required to obtain confirmatory test results from a number of patients that are below threshold, patients that are above threshold, in order to select an appropriate threshold. But this technique does not require those test results prior to activities. It does not rely on a rigorous scientific method, but allows for an agile and flexible approach to adapt the threshold as needed. So first, let's talk about the initial threshold selection. There are three different options for initial threshold selection. One is matching the CAD to an expert reader's sensitivity for TB, and I'll describe that in some more detail. It's also possible to match the CAD to the confirmatory testing capacity, so determine the maximum number of tests that can be performed and matching the CAD, at least to start with. And then you could use a best guess option. This is based on other people's experiences, any publications that are out there, discussion with experts or the supplier's recommendation. So I'll describe each of these three options. First, let's start with matching CAD to an expert chest X-ray reader. So this matches the CAD performance to an expert reader, which is one of the traditional standards for TB screening and triage. There are certain requirements for this approach. First, an expert chest X-ray reader needs to be available prior to the start of activities. Ideally, this would be a local radiologist or specialist with the most expertise in TB. It's preferable to have a local radiologist, someone who's familiar with the context, familiar with the comorbidities, and is experienced at reading chest X-rays for TB in the region. If a local radiologist or specialist is not available, it's possible to use a remote radiologist or a remote specialist, someone who has expertise in TB, if there's a way to transfer the images remotely so they can be read. Also, what is required is a set of digital chest X-rays. We would recommend a minimum of 200 X-rays. These X-rays need to be from the same X-ray machine that will be used with CAD and from a similar population in which the screening will be done. And these need to be available prior to the start of activities. So the CAD scores will be recorded from the set of X-rays. So for example, 200 X-rays. And it's possible to match the CAD performance to the expert reader's sensitivity for TB to select the initial threshold. I'll describe in our country experiences how exactly we did this. It's also possible to set the initial threshold based on the confirmatory testing capacity. So regardless of which technique you use, it is important to determine the maximum number of confirmatory tests that can be performed, because this is a number you don't want to exceed this number, and that can be important in selection of your threshold. The testing capacity could be related to costs. It could be related to the number of testing machines available. It could be related to the consumable availables, or even the HR capacity to perform the tests. Also, it's important to note that this testing capacity isn't necessarily fixed and may change. For example, if additional gene expert machines are purchased or additional staff is hired, the testing capacity can increase. But it's important to keep this in mind when we're selecting our threshold. So as mentioned, this can be used to select our initial CAD threshold. We can set the threshold to estimate the number of individuals above threshold to equal the maximum number of confirmatory tests available. Basically, this will be the lower limit of threshold. Using a lower threshold than this will refer too many individuals and overwhelm the testing capacity. The one downside of this is that it will use more confirmatory tests, but it's a way to set the initial threshold, and then we can adjust as we go along through data collection. The third method, this is the least desirable, but sometimes it's necessary, is the best guess. So we can use discussions with other experts, similar experience from other implementers, if there are any existing publications using the same CAD product and see what threshold they chose, or the supplier's recommendation. But basically, overall, because our method allows for threshold adjustment, selecting the perfect threshold is not as important as identifying a reasonable threshold that will allow the start of CAD activities without delay. So the second part is threshold adjustment. So after the initial threshold is selected, we can start to use the CAD and then use the data to decide if the threshold needs to be adjusted. Basically, the way this works is we collect the data and track certain indicators. Examples of indicators would be screening positivity. So this is the percentage of individuals referred for testing, or in other words, the percentage above threshold. Test positivity above threshold. So looking at the individuals above threshold, what percentage have a positive test? And then test positivity at the threshold. So the percentage of individuals at the threshold with a positive test. So based on these indicators, then we choose our targets. And let me give you some examples of some targets. So for example, 20% screening positivity, 10% test positivity above threshold, 3% test positivity at threshold. And this will become more clear when we start to go through some of our country experiences. So we have our target and we have our indicator, and we need to compare the two to decide if the threshold needs to be adjusted. So we developed a simple table looking at the different indicators, looking if the indicator is less than the target or greater than the target, and whether we should increase the threshold or decrease the threshold based on these results. There's no formula to determine exactly how much to adjust the threshold. Some general rules are, if it's a small difference between the indicator and target, you can do a small adjustment to the threshold, maybe 2 to 5 points. If there's a larger difference between the indicator and the target, you may choose a larger adjustment, for example, more than 5 points. Frequency of threshold evaluation. In general, we evaluate more frequently at the early stages when we have less certainty about the threshold itself, about the performance of the threshold. And once we have more data and we're more confident in the performance of the threshold, we can evaluate less frequently over time. This is just an example of evaluation intervals. We can do it by number of chest x-rays or a time period, 500, 1,000, 2,500, 5,000 x-rays, or 2 weeks, 1 month, 3 months, 6 months. This is just an example of evaluation of intervals and something that we've used as a guide in our country experiences. But the timing of the threshold evaluation is flexible. For example, if you do decide to change the threshold significantly, you may want to evaluate again after a short interval without waiting another 6 months because you have just changed the interval. So this is up to the program to decide when you're going to check the threshold and when it's convenient for you as well. So now I'll talk about some of our country experiences. with CAD threshold selection in MSF. Our first implementation was in the Philippines, which is a country in Southeast Asia with a population over 110 million. High prevalence of TB in the country, with more than 500,000 estimated to have developed TB in 2020. And the objective of our project was to do TB active case finding and contact tracing in a densely populated urban district of Manila. And we were looking specifically at the Tondo district. You can see from the photos of the Tondo district how crowded the district is, how close the buildings are together. So active case finding was started using a mobile X-ray van and a radiologist on site before CAD implementation. You can see in the photo in the upper right, that's our ACF site. We used a basketball court, which gave us plenty of room for all the different the entire circuit for the ACF, and our radiologist tent, which was part of the ACF circuit. Using the X-ray van allowed us to move to different ACF sites to allow us to screen the entire district. And this was our ACF circuit. We had patient registration, symptom screening, chest X-ray. We did sputum collection on site. We also had a physician evaluation on site and exit registration. So after 4 months of ACF, CAD was integrated into the circuit. This is a photo of our mobile X-ray truck with digital X-ray. Inside the truck, you can see the X-ray machine towards the front and the X-ray computer towards the back. And we connected the offline box with CAD for TB version 7 from Delft Imaging into the X-ray van. It's hard to see in the picture, but there's the CAD box. It's quite small, about the size of a hard drive, and easy to connect to the X-ray computer. So in terms of CAD threshold selection, there were some general considerations before we selected our threshold. We did have discussions with some experts and the supplier, and we learned that CAD for TB version 7 likely required a lower threshold than CAD for TB version 6. There had been some publications out on CAD for TB version 6 that they were using a threshold of 50 or 60. And so we knew that most likely we would need a threshold lower than that. Also, from our ACF activities before CAD, we realized that the TB prevalence in the Tondo district was very high. 5% rate of microbiologically confirmed TB during ACF activities before CAD. And because of this, we decided that we would likely choose a lower CAD threshold. We really wanted to maximize our sensitivity for TB. And so these two considerations, it was helpful for us to know this even before implementation. So in terms of calibration methods, we did consider the WHO TDR toolkit, but we did not have the time or the resources to invest into the protocol. So we decided to use our own approach based on reactive adjustment. So as mentioned before, there are 2 steps involved: initial threshold selection, threshold adjustment. And before starting, we also needed to determine confirmatory testing capacity. So after discussions of the team, we determined that a maximum of 30 sputum samples per day could be sent for gene expert testing. This was based on an agreement with the local authorities. After several months, we did purchase an additional gene expert machine to increase our testing capacity. And this became essential when the screening increased to 150 individuals a day. So an example of how the testing capacity is not necessarily fixed. So these were the options mentioned before for initial threshold selection. We prefer to use number 1, if possible, matching CAD to an expert reader's sensitivity. And this is the method we used in the Philippines. So the way we did this, first we needed to make sure we had the required elements. Expert chest X-ray reader. We had the benefit of an on-site radiologist who was reading all the chest X-rays during ACF before the CAD. We also had a set of 650 chest X-rays from the X-ray van during ACF before CAD. So this is what we would use to set our threshold. We recorded the CAD scores from 650 chest X-rays and matched the CAD to the local radiologist sensitivity for TB to select the initial threshold. Now, how do we do that? We could see from the data that the local radiologist is referring about 35% of ACF participants for testing. So we chose a threshold of 25, which would expect to also refer 35% of participants for testing. This was based on looking at the CAD scores from the 650 chest X-rays. So the initial threshold of 25 was selected. Another benefit of matching the CAD to the local radiologist is there would be no major change in the workflow, no major change in the number of referrals for testing. So the number of patients referred, the number of sputum samples collected would be approximately the same before and after CAD. Also, we were hoping that this would increase acceptability of CAD by the ACF team. If the CAD was performing similar to the radiologist on site, we thought that it would be more acceptable for them. It was a new technology and they had some reservations at first, but we wanted to make sure that they agreed with using this. So considering our gene expert testing capacity, 35% referral rate based on a threshold 25 is acceptable as long as the number of ACF participants is less than 85. If it becomes more than 85, we're going to overwhelm our testing capacity. And at this point, when we reach these higher numbers, we purchased an additional gene expert machine to increase our testing capacity. So the second step here is threshold adjustment. In order to do this, we looked at the data at periodic intervals. As mentioned, we wanted to look our first evaluation to be shortly after implementation. So in this case, we evaluated just 2 weeks after first implementing the CAD. We chose a target. Our target was 35% screening positivity based on the local radiologist sensitivity. So after looking at the data, after 2 weeks, there was a 39% screening positivity at the threshold of 25. So in this case, the indicator was greater than the target. And if we go back to our chart here, looking at screening positivity, indicator greater than target would indicate for us to increase the threshold. So in this case, we increased the threshold to 28. And we could see based on the data that at a threshold of 28, the screening positivity would be about 33%, so closer to our target of 35. Our second threshold evaluation was at 1 month. Again, we chose a target of 35% screening positivity. And the data showed 34% screening positivity at a threshold of 28. So this was acceptable to us. The indicator is close to the target and our threshold was maintained at 28. We had our third threshold evaluation at 4 months. Once again, we chose a target of 35% screening positivity. Once again, the indicator was 34% at threshold 28, matching the target, and so the threshold was maintained at 28. For our fourth threshold adjustment, this was at 11 months. We changed the target. So we changed it to 3% test positivity at threshold. And I'll show you how we did this. First, we compiled this table looking at gene expert positivity rates based on the CAD score. And we could divide it by decile. So you can see there's very high correlation with the CAD score and the percent expert positivity. So if we're looking at a target of about 3% test positivity at threshold, we're looking somewhere in this range. So somewhere in the range of 20 to 40. Now we can break this data down. We have enough data to break it down into smaller intervals of CAD score close to the threshold. You can see that at the current threshold of 28, the test positivity at threshold, it's about 1.4, 1.5%. So this is lower than our target. So that's our indicator. Indicator is less than our target. So based on the table, our threshold should be increased. Now, where do we increase our threshold? The benefit of using this indicator, test positivity at threshold, allows us to be a bit more precise about where we're setting our threshold. If we look at 32, a threshold of 32, this gives us a threshold percent positivity somewhere between probably 2 and 3% looking at the data. So this is close to our target of 3%. So we decided to choose a threshold of 32, and this would match our target. We repeated the same exercise at 16 months. So once again, we chose our target, 3% test positivity, and this was just something we decided as a project. There's no gold standard for this, and this will vary. This number can vary depending on what your programmatic goals are. But 3% test positivity to us was acceptable. So looking at our data again, so this is updated data, looking at these CAD score deciles. Again, if we're thinking of our target of 3% test positivity, we're looking at this range once again, 20 to 40. Our threshold, ideal threshold is somewhere in that range. Another thing to point out here is the difference that choosing the threshold can make. If you look at a threshold of 30, for example, versus a threshold of 50, you can see that using a threshold of 50, we would miss approximately 150 individuals that have TB. So these differences in threshold can really make a difference in the performance of our CAD. So let's break this down once again, looking at smaller intervals right around the threshold. So we have a threshold of 32, which is what we're currently using, right about here. And you can see that our indicator, once again, is somewhere around 2 to 3% test positivity at a threshold of 32. So our target meets our indicator, and we kept our threshold at 32. So some of our overall results from the Philippines project, which is still ongoing. CAD has helped screen over 20,000 individuals in the district for TB since November 2022. This number is probably closer to 25,000 because this was from a few months ago. CAD has helped decrease the turnaround of the ACF circuit by 50%, which allows us to screen twice as many individuals. So it's really had a significant impact. And 4.5% of these 20,000 individuals have been found to have microbiologically confirmed TB. So these very high rates that we were seeing initially have been maintained after more than a year and a half. Also, interestingly, 63%, so nearly 2/3 of individuals with microbiologically confirmed TB did not report symptoms. So this highlights the importance of chest X-ray and CAD in the screening process, and that you can't rely on symptom screening alone. Multiple other studies have shown the same thing, that chest X-ray is more sensitive than symptom screening. So this is just a photo of the physician on site using the CAD in Philippines during active case finding. They're looking at the digital chest X-ray on the left and looking at the CAD image on the right at the same time, using the CAD score to decide for patient referral. It's definitely an example where the CAD has been smoothly integrated into the screening activities and where it's had a significant impact in this project. Our second CAD implementation was in Tajikistan. This is a small country in Central Asia with a population of just under 10 million, and 8,000 estimated people developed TB in 2020. So for our screening project, our objective was to screen the population of a remote district for TB through active case finding activities. We used a mobile radiology unit that could be transported to different locations and reach some of these remote areas using just a land cruiser to transport the equipment. So in this project, we use an ultra-portable X-ray, the Delph Lite, with CAD for TB version 7. And the ultra-portable X-ray and CAD could be assembled and disassembled before ACF and after ACF. It takes about 20 minutes for the setup. And using this approach really allowed for a flexible and versatile setup. So basically anywhere we had room to set this up, an empty clinic room, a school, any place where there's space enough for us to set up the equipment, we could use for screening activities. So our ACF circuit, patient registration and symptom screening. There was a lot of paperwork involved before we using CAD, and this was all converted to digital. The chest X-ray and the CAD. So the ultra portable machine setup. The image was immediately transferred to the laptop computer, which was connected to the CAD box, and all the analysis could be reviewed on the laptop. And the physicians were in the next room with a tablet where they could evaluate the CAD score and the X-ray and talk to the patient and make their decision about referral for gene expert testing. So in terms of reactive adjustment, going through our 2 steps, initial threshold selection, threshold adjustment. So before we do this, we need to determine confirmatory testing capacity. So all the ACF participants suspected of TB based on the CAD score were referred to a local facility for confirmatory testing. And based on discussions with the local facility, that testing capacity was determined to be about 20 tests per day. We didn't want to exceed this number. So let's go through our options for initial threshold selection. So once again, we used our preferred option of matching the CAD to the expert chest X-ray reader's sensitivity for TB. So looking at the requirements, we did have an expert chest X-ray reader. We had an on-site radiologist who had experience with TB before CAD implementation. And we also had a set of digital chest X-rays. So we had 142 chest X-rays from ACF using the ultra-portable machine. This was before CAD. So we recorded the CAD scores from these 142 chest X-rays and matched the CAD to the radiologist's sensitivity for TB. The radiologist referred 9 of these 142 chest X-rays for testing, so about 6.5%. So we matched this with a threshold of 40, which would also refer approximately 6.5% for testing based on our evaluation of the CAD scores. So our initial threshold was set at 40, and this would be within our expert testing capacity. So next, the threshold adjustment. Our first evaluation was done at 1 month, and we used as a target this 6.5% screening positivity. The data showed 6% screening positivity at a threshold of 40. This was close enough to us, the indicator close to the target, so we kept the threshold at 40. Our second evaluation was done at 3 months. So our target, once again, was 6.5% screening positivity. In this case, the data showed 3.2% screening positivity at a threshold of 40. So much lower than before, and we weren't exactly sure why. So the indicator was less than the target, and looking at our table, we're looking at screening positivity, where the indicator is less than the target, and the table suggests to decrease the threshold. So we decrease the threshold to 35. Our next evaluation was done at 12 months. kept the same target, 6.5% screening positivity. And the data showed 3.5% screening positivity, even though we had lowered the threshold to 35. At this point, we were questioning the reliability of the data. We knew there were some issues with the data collection, so we weren't entirely sure if this was accurate. But according to our method, the indicator less than the target, so looking at our chart, screening positivity, once again, indicator less than target would indicate to us to decrease the threshold. So we decreased the threshold to 30. Our next evaluation was done at 13 months, so just 1 month after, because we really wanted to see what was going on. We wanted to see if the data was reliable, and because of these different changes in threshold, we wanted to see how the CAD was performing. However, at a threshold of 30, we quickly found out that the number of referrals for expert, so basically the numbers above threshold of 30, was greater than our expert testing capacity. So that's our limit. We can't go any lower than that. And in fact, we have to increase our threshold because we can never exceed our testing capacity. So in this case, we increased our threshold back up to 35. So some of the takeaway points from this experience, these small changes in threshold can really make a large difference in the number of referrals for testing. So just decreasing from 35 to 30 overwhelmed our testing capacity. And just to emphasize that it is very important to consider our testing capacity throughout the process. Whenever we're deciding on a new threshold or adjusting the threshold, we have to consider whether this will allow us to remain within our testing capacity. But because we're using this reactive adjustment technique, we can be agile, we can be flexible, and we can make rapid adjustments in the threshold as long as we're collecting data. Another thing this experience has highlighted to us is the importance of reliable data collection. We weren't sure whether we could really trust the data here, but we did the best we could with what we had. And this is something that's important to keep in mind, that it is very important to have good data collection. So in summary, this is a practical method of CAD threshold selection that I've described today based on reactive adjustment. This allows for adaptation of the threshold based on periodic evaluation of data. Because the method allows for adjusting the threshold, we can select a reasonable initial threshold. It doesn't have to be perfect, but we really want to be able to start CAD activities without significant delay. We can use this in settings with limited availability of resources. As mentioned in the beginning, confirmatory test results are not required prior to starting activities. And this flexible approach allows the project to define its own targets, change its targets, and rapidly adjust the threshold depending on programmatic goals. Just to highlight some of the challenges that we've experienced using this technique, it does require some preparation before CAD implementation and certain requirements, such as availability of an expert reader, availability of chest x-rays. In general, we recommend a minimum of 200. So maybe in Tajikistan, we had lower than ideal. However, if you didn't have these available, it's also possible to start activities until you reach 200 chest x-rays, and then you can go back to use one of the options for initial threshold selection. As mentioned, it's essential to determine the testing capacity, but this can be variable. It can change, and sometimes it's difficult to define exactly what the testing capacity is. It depends on the number of individuals screened, how many you're going to refer for testing, and you may not know the number of individuals you'll screen on a given day. Reliable data collection is very important. The data collection itself is quite simple. It just relies on CAD scores correlated with confirmatory test results. But we need a way to do this, preferably in a confidential way using patient ID and not patient identifiers, but a way to collect this reliably so we can do our data evaluation. But we've realized it can be a challenge. test positivity at threshold. This is the technique we've used in Philippines, and I think it works quite well. It allows identification of a more precise threshold, but it does require a large number of individuals screened and a large number of positive tests in order to look at the data and for the data to be meaningful. So thank you very much for your attention, and a special thanks to the MSF teams in Philippines and Tajikistan for all their work.
Thank you, Juno, for your excellent presentation. Y a continuación, y la última presentación,
Next, the last presentation will be the country experiences, in this case Paraguay, where the TDR tool was used to determine the cutoff point. Angélica.
Hola, ¿pueden ver ahí?
Ponerlo a modo de presentación, Heli.
Sí. Ahí
Ya,
está. ¿Está a modo de
adelante.
presentación?
Adelante.
Perfecto.
Please go ahead.
Gracias. Bien, muchas
Thank you
gracias,
very much.
Ernesto.
I
Gracias
thank you,
también a
Ernesto, and
OPS
also I
Regional por
thank
la invitación y
Bajo
por este tipo de
Regional for the
espacios en
invitation and also
donde
for this type
podemos
of
compartir también nuestras
opportunity to
experiencias
share
en
our
los diferentes
experiences
países
in the
y de
various
paso también
countries, and
aprendemos todos.
also we learn
Bien,
from everyone.
lo que voy a presentar ahora es
I
precisamente
will
nuestra
be presenting
experiencia
indeed our
utilizando
experience
esta herramienta
using this
para
tool
establecer el punto de
to
corte. Esta
establish
es una
the cutoff
herramienta, como
point.
ya lo
This
estuvo
is a
mostrando también
tool, as
Cecily,
Cecily
OMS
already showed,
PDR.
that
Y en
belongs
este
to
caso voy a
WHO
presentar nuestra
TDR, and I
experiencia
am
para los
going to
dos
share
equipos
my
de
experience
radiografía
for
digital que
the
tenemos
two
con sus
digital
respectivas
radiology
tecnologías.
or radiation
Luni, que
teams
es
we
para
have
Fuji, y
with
CAD for
various
TV, que es
technologies,
para
Luni and CAD for TV for
Bien.
Delft.
La
Now,
doctora Sarita ya estuvo
Dr.
presentando
Sarita has
algunos de estos
already
datos en lo que
introduced
fue la reunión anterior,
some of this
pero a
data
modo de
in
que
the previous
podamos tener
presentation, but
contexto
so as
y
to
si por
offer
ahí
some
hubo alguno que no
context,
pudo
and in
participar,
case there was
entonces,
someone who
y para
was
refrescarles la
not in
memoria,
attendance, and also
les
to
muestro
refresh
estos
your
datos.
recollection,
La
I am going
población
to
de
share this
Paraguay,
data.
que es
The
alrededor de
population of Paraguay is about
6.947.270, esto para el año 2023,
6,947,270
y donde
inhabitants.
hemos
For
notificado en el mismo
2023, we
año
have
una
reported
incidencia
in
de
the same year an incidence of
48.8 casos por
48.8
100.000
cases
habitantes.
every
Así también tenemos nuestras dos
100,000
poblaciones
inhabitants. We
clave,
also
que
have
son
our
la población indígena y la
two key
población privada de
populations, the
libertad,
indigenous
donde
populations and
pueden observar aquí
also
las
the
incidencias que tenemos
prisoners.
para cada
And
uno,
here we can
en
show
donde
the
para
incidence
indígena
we
tenemos
have.
una
For
incidencia de
indigenous population,
310
we have
casos por 100.000
310 cases
habitantes,
every
y esto
100,000
representa
inhabitants,
un
and this also
11%,
represents
la población indígena, un
11% of
11%
the
de todos los casos de
indigenous
tuberculosis que hay
populations
en
of all of
Paraguay
the
para el
tuberculosis cases we
2023,
have in
y así
Paraguay
también
for
la
2023,
población privada de
and
libertad,
also
que
for
representa un
prisoners,
22% de todos nuestros
people in
casos de
prisons, that
tuberculosis
is 23%
reportados
of all of
también
our
para
TB
el
cases
mismo año.
reported also for the same year, that is to
Y en
say
cuanto a lo que es
2023.
tamizaje de
And
la
as to the
tuberculosis, venimos
screening
trabajando en
of
Paraguay
TB, we have
haciendo
been
búsquedas
working in
activas desde el
Paraguay by
año
means of
2016,
active
en
case
donde
detection,
cuando
active case
comenzamos
findings,
2016 a
and we
2021,
started in
hacíamos
2026,
búsquedas activas
2021.
según la
We had
clínica del
active
paciente.
case findings
Esto lo
depending
hacíamos desde
on
el
the
Programa
patient. We
Nacional de
did it from
Tuberculosis
the
con el equipo
TB
del Programa
program
Nacional de Tuberculosis.
using the
A
team
partir de
itself.
septiembre de
And
2021
as of
inicia un
September
proyecto por
2021,
parte
we
de un
started with a
consorcio que se
project by
denomina
means of a
EUSAT,
consortium known
que es un
EUSAT.
proyecto
And this is a
pilot que se
project
hace en las cárceles. Se hizo en
that
3
we carry
cárceles en
out in
Paraguay.
prisons. We did it in 3
Y
prisons in
para mayo de
Paraguay.
2022 ya
And
el país
May
adquiere
2022, the
equipos para
country had
radiografía
already
digital
obtained
con
equipment for
detección asistida por
digital
computadora,
radiation
y comenzamos
that
el
was computer
tamizaje ya
assisted, and we
utilizando
started
esta
with the
tecnología.
screening using
Para
this
esto lo
technology.
hacemos
To
desde el
this
nivel
end, we
nacional,
do it
desde
from
un
the
equipo
national
que
level
dirige el
using
programa de
a team
tuberculosis,
with
y
the
para esto
TB
se hace una
program, and we
coordinación
also
con
coordinate
las regiones sanitarias, con
with
los
the
servicios
health
regionales,
regions and the
distritales y
regional
locales.
district services as well as the local
Estos
services.
son los dos
These
tipos
are
de
the two
equipos
types of
con los que
equipment
contamos en el
that
país.
we
Tenemos
currently
dos
have
equipos
in the
Delft que
country. We
cuentan
have
con
2
la
Delft
tecnología CAD for TV
pieces of
actualmente,
equipment
ambos
that
en la
have
versión
CAD
7.
for TV
Y
in
tenemos
7
dos
version,
equipos de
and
Fuji
we
que
have
tienen la
2 Fuji
tecnología
pieces of
de
equipment
Lunit.
with the Lunit technology. And to remind you where we carry out our screening, we do it with everyone that goes to health centers and also in prisons, where you saw we have a very high incidence of TB. We also do it in households. We also have mass campaigns for TB screening in remote areas and also within the indigenous populations, farming populations, and also within the community, as well as sporadic activities that are sometimes requested, and there we go. What is the algorithm we use? We use the parallel screening. Therefore, we screen the population, we ask about TB symptoms that they may have, and if they accept, we take an X-ray, a chest X-ray using AI. If the symptoms and the chest X-ray show that one or both are positive, then we refer the patient to be sampled for gene expert. If the screening is negative, then the patient has to be assessed based on the criteria we have for preventive therapy. This is the form that we have created to gather all of the data that is related to the screening. We have an epi-info form. This is the first section where you can see the data that we collect for screening. And this screening, as I mentioned, started in 2022. This is what we called the first stage, and the sequence of the circuit that we applied is the one that we see on the screen. We have a first table where we recorded all of the vital signs. We took all of the data from the patient, then they moved on to the second table where we took blood samples to obtain, for example, rapid HIV testing, syphilis, and diabetes. And later on, they moved on for the X-ray. And after they had their X-ray, chest X-ray, they talked to a doctor. And finally, they moved on to the last table that was for sampling based on criteria, if they met that criteria. And also for the second stage, here we are applying this work method where we take all of the data, all of the vital information for the patient, and then the second table goes to radiology and finally to gene expert. Here you can indeed see the images of what we obtain with the X-rays and chest X-rays and also the equipment that we use. Now, moving on to the tool for obtaining the cutoff point. This is something that Cecily had already shown. This is the link for you to have access to the tool. Once we have access to this point, the first screen we see is this one that we have right now on the screen. We also have various tabs. The first one is the instruction, the one that we see here. The second tab shows us the space to upload the data. The third one gives us the ROC information. Next, we have the decision-making table. The next one shows us the subpopulation, where we can also select our subpopulation, that is to say, the population that we'd like to study to determine the cutoff point for prisoners, indigenous population, or people that have diabetes. And then we have the last slide, the last tab that shows us the information for the population, that the subpopulation that we have selected. This is all related to the introduction of the tool. This is indeed what Cecily had shown, the document that we used, and also the general considerations that we had to select the cutoff point. First of all, I should mention that based on all of the information that we collected for the screening, it is also necessary to prepare 2 Excel files with the CSV format, including the information for the screened individuals. This Excel sheet can be downloaded from the page itself. where you will find the tool where there is a model to download with all of the information that is needed and also the headings. So we prepared 2 Excel sheets because or files because we have 2 pieces of equipment, CAD for TV, as I mentioned, that is used with Luni, and the second one for Fuji. One is for Delft and the other one for Fuji. So the period is January to December 2023, and to prepare the files, we followed the instructions that are part of this document, and we also included, in addition to the suggestions by the tool and also the Excel that can be downloaded, we also included key populations such as prisoners, indigenous population, and also people that have diabetes and those contacts that are and those that had contact with someone with TB. As you see, these are the variables that are requested to be able to upload the data to the tool. And this is in the A section of the document that we have here, and you can also see the variables that are needed to be able to obtain the data. We have patients that are shown here in numbers, and the CAD numbering or score from 0 to 100. And here I would like to mention, when we started to test the tool, we had some difficulties, and we realized that the main difficulty was that in some cases we obtained a score in decimal system, and this had to be moved to whole numbers so that the file could be read and we could have the whole process. So this has to be taken into account. We need to round up if this is in decimal format. Then we also have the classification for TB. Here, this shows the different coding in this tool for the age groups of those that are between 15 and 65 years of age, and those that are older than 55, the earlier history of TB, whether the person has HIV, and also the person has diabetes mellitus, and also whether the person is a smoker or not. This is our database with the organization. You saw that we obtain the data in EPI info. We obtain all of the information that we request from the patients, and we also ask whether if the patient is from the indigenous population, we ask what population they belong to, whether the woman is pregnant or not, and as to the population, whether we're talking about smokers, former smokers, or if the person never smoked, whether there are any contact with a TB patient, with any previous TB, and also this is the score result. As you can see here, there are some here with decimal numbers, and we need to change this to whole numbers so that we do not have any problems when uploading this document to the tool. The CAD report in GeneXpert, whether it was carried out or not, the result, and also the culture. We did this with some patients. The GeneXpert team, rather the X-ray equipment used, Delft for Fuji, and also the case definition, if at the end of the day it was a confirmed TB case or not. But what we upload to the tool is exactly this. That is, this is what is requested. You can download, as you can see it here, you can download this template that you fill in with the screening data. And this was precisely what we did. Once we prepared the Excel sheet, we did one, as you can see, for Fuji and the other one for Delft. This is what we gathered in the tool. What else we considered? We saw that the included population that was screened with Fuji Lunit accounted for 5,666. We had 683 with Delft, and since the number of screened individuals with HIV was very low, we were unable to obtain data to chart the ROC curve and also to obtain the decision table. This is for CAD for TB. As to populations with contacts, diabetes mellitus, and those that were screened with CAD for TB, the number was very low, so we could not obtain the decision table, but we did obtain the ROC chart. I would also like to mention here that we have established a cutoff point taking into account the sensitivity that is close to 80. This is for LUNIT and also for CAD for TB. And here I would also like to mention that this is part of a process. We are learning here as a country. We are learning here on this tool, about this tool, and also as to how to establish this cutoff point. But what we have considered in this case is precisely our testing capability, our gene expert capability, considering that Paraguay has made gene expert use universal as the initial diagnosis for all of the suspected TB cases and also for symptomatic respiratory cases. Therefore, we have sufficient gene expert pieces of equipment in all of the health regions in the country and also cartridges to conduct the testing.
So this is a sensitivity rate of about 80 with these decision tables that I'm going to show you now. Now, generally speaking, this 25 threshold, 40 for CAD for TB, although we do have a specific cutoff point or threshold for specific populations. You're going to see the differences that you can observe in these results regarding populations, cost, sensitivity, and specificity. Now, as I was showing you, this is the tool. The data is thrown into this tab. And so here we have a CSV template. You have to put in the size of the population, the TB prevalence for 100,000 inhabitants, and the cost for the confirmation for the TB test in dollars. These were the parameters that we used for the overall population. Bearing in mind the size of our overall population, the prevalence of 54 cases per 100,000, and the cost of $9 for this test. Now, so for populations, our inmate population, you can see the number of inmates that we have. The prevalence is 5,119 cases per 100,000, and the cost is the same for all of the populations, $9. The same regarding indigenous populations with a prevalence, as you saw, the same for mellitus and TB contact. These are the parameters that we used, and I will now show you that that information then would be put into this first tab where the data is inserted. Let's take a look at the results that this tool gave us, especially the decision table. Now, this is how we did it. First, for the general population and with the Fuji equipment, which is the unit technology, uses the LUNIT technology. The sensitivity was around 80, as you can see here, as we've indicated, a threshold of 25 in the overall population of 7.5 million, the prevalence of 54 cases per 100,000. As you can see, we have a sensitivity bordering on 80%, 79.8, and specificity of 83.5. This then, we would lose 824 cases would be missed, 20.2%. I also want to show you what would be the total cost to confirm TB and how much per case? 3,937 per case for the general population. That with the Fuji. Now with CAD 4TB, let's compare. You saw that the 25 was the threshold with Lunit. Now it's 46 is the threshold or cutoff. You can see that 680 cases are lost, 16.7%, and the cost for confirmation per case is 2,225. Quite a difference between Fuji and Delft regarding profitability. Now, indigenous population using Fuji, a 38 cutoff, sensitivity is 79.4 and 83.9 for specificity. We would miss 90 cases, and the cost of using Fuji for the indigenous population would be 603 per case. Here, we can see the indigenous population using CAD 42B. 46 is the threshold, and so we have a sensitivity of 83.3% and specificity of 70%. We would miss 77 cases, and it would cost us 453 in this indigenous population using CAD 4GB. Now, inmate population or person deprived of liberty, 24 is the cutoff, with a sensitivity of 79.4, specificity of 80.7%. We would miss 184 cases, and it would only cost $53 to administer this test using Fuji in inmates. Now, diabetes mellitus, 74 is our cutoff. A big difference from what we just saw. 80% sensitivity, specificity of 94. We would lose or miss rather 110 cases, and it would cost us 1,184 to confirm cases for diabetes mellitus. Contacts, again using Fuji. 35 is the cutoff, 80% sensitivity, 84.7 specificity. We would miss 43 cases, and it would cost, using Fuji, 109 per case. That's it. As I said, we were not able to produce the decision tables for the remaining specific populations with CAD 4TB because we had a very low number of persons who had been screened. We're going to continue working on that. It's quite worthwhile. That is what we have, what everyone else who spoke for me have shared, saying that this evaluation should be done every so often to adjust the cutoff point. The interesting thing here about this tool, we think we still have a lot to learn regarding all the features or utility we can get from it, because we saw quite interesting results that are helpful in decision making. That concludes my intervention. Thank you.
Gracias, Angélica.
Thank
Vamos
you,
a dar
Angélica.
paso ya a la última sesión que
The last
corresponde con preguntas y
session
respuestas.
is for
Y le damos la
Q&A.
palabra a nuestra colega Becky Marcelino. Adelante,
We give the
Becky.
floor to Marceline.
Gracias, Ernesto. Muchísimas
Thank you,
gracias a
Ernesto.
nuestros panelistas
And I
de la
thank all
segunda
of our
sección del
panelists
cálculo
of the
del
second
score o punto de
section
corte para
for
CAD,
the cutoff point
específicamente para
calculation
diagnóstico de TB.
for TB diagnosis. And both strategies that have been shown today, we see how important it is to have an active search plan, enabling us to identify what percentage of sensitivity we have to calculate for. Both methodologies are user-friendly, easy to use in our countries with information we have. And if we look at the questions that we have in Q&A, we have a number based on this tool. Ivan Cardosa asks, can artificial intelligence be used?
De otra generación y SEO sería utilizar la estación de lectura. Esta pregunta creo que la vimos en los webinars
Alone,
anteriores.
AI can be used alone without X-ray compatible X-ray machines. That is, using equipment of any other generation as a reading station. We need to be able to read this.
Lo que debe estar seguro que
What you have to be certain about is that the image be in the DICOM protocol. Now, Mary Hatton asks, there is a cutoff point of the incidence rate, and or is there an incidence rate at which you would recommend the chest X-ray for screening?
Históricamente, en evidencia de que la radiografía es un método de tamizaje.
Based on evidence, the X-ray is used as a screening tool. I would like to ask our panelists some of the questions that are in the chat. How did you calculate the cost of each TB case using that tool? Perhaps Cicely can answer.
Hello, I was just going to respond to the question about is there a general incidence at which screening should be done in the population? And there's not incidence, but there is a WHO recommendation that general community-wide screening can be done at a prevalence of 500 per 100,000 or 0.5% or higher. Basically because that is when the trade-off of risks and benefits, like the first speaker was talking about, go in the favor of screening. So I think that's a point that we can think about. Can you explain again what the second question was? I didn't catch it.
The second question
el costo que tiene la herramienta
is the cost of the tool, the TB tool. What are the variables used to calculate the cost? Does that include HR cost? Transportation cost?
The cost. Okay.
Transportation, is that also included in the TB cost that's calculated?
The cost estimates from the TDR toolkit. These are purely diagnostic testing costs. So when you are using the tool, you'll enter a value or a unit cost for how much one diagnostic examination costs. And the tool then essentially just multiplies that by how many people you'll be referring for diagnostic testing. So this is a very good point to bring up. It's a limitation that this tool is not doing extensive costing analyses. It's just doing unit cost calculations for the implications of different CAD thresholds on the number of people who go on to diagnostic testing and the cost for that based on the per unit diagnostic testing cost. So I hope that answers the question.
Thank you. Sí. Tengo otra pregunta.
Another question.
Gracias, Cecily.
Thank you, Cecily. This is for Angelica. Two questions. Did you use hemoglobin, glycosylate hemoglobin for the diagnosis of diabetes? And also the matter of cost was just addressed.
Sí, con respecto al costo, ya mencionó
justamente
Cecily que
Cecily
eso lo
just
hace solo la herramienta.
said that that is
Con respecto a lo
done
primero,
by
sí,
the
es lo que
tool. That's all it
utilizamos.
does.
Eso
And
lo hicimos
yes,
en
we
la
do
primera etapa,
use
pero ya
the hemoglobin in the first stage.
no lo estamos haciendo,
We're not
ya es
doing it.
simplemente tomar los datos de filiación del
We
paciente,
just
hacerle
take
la radiografía de tórax y
the
remitirle para
X-ray of the
hacerle la prueba
patient,
de Gene Expert.
and we send that to the gene expert for testing, as well as the data regarding family history.
Entonces, dice una pregunta en el chat, perdón,
Here's
que
another question.
podría decir que a construir una base de
In putting together a database for AI to ascertain the sensitivity and specificity of the test. Now, to assess the sensitivity and specificity, that is going to depend on whatever plan you have. If your goal in the active search plan is to reduce the coverage by 80% in the diagnosis conducted, that will enable you to choose the most appropriate diagnostic methodology. We have other colleagues here that perhaps would like to add something to that. To increase the sensitivity of the screening, what can be done? Josephine?
Las recomendaciones para aumentar la sensibilidad
for increasing the sensitivity of the active search for cases.
Is this question for me? Sorry, I didn't capture.
Sí, por favor.
Yes. Okay. So how to increase the sensitivity of your screening?
Yes.
Yes. Okay. So in general, if we're talking about screening done with X-ray, we're already in a very good place because this is the most sensitive screening approach that we know of right now. So this is already the best approach that we know in terms of capturing the most prevalent cases of TB through a screening approach. And as Juno mentioned today, and as we've mentioned before, X-ray screening is going to find a large portion of cases that don't present with symptoms. So we're already much improved over symptom screening. So then beyond that, we've seen a lot of data and a lot of examples today on how CAD can be used to improve the sensitivity of chest X-ray screening. This is, I think, one advantage of CAD over human interpretation of chest X-ray. We haven't really talked about this yet, but that CAD can be changed essentially infinitely between 0 and 100 to decide how you want it to perform as a screening tool. Human readers can adjust how they read at X-rays to a certain point, but I don't think they can be adjusted quite in the specific way that CAD can be. But as we saw, again, quite a few examples today, the threshold for CAD can be set very low to maximize the sensitivity of screening. And there is often a point at which you can set it that you will capture 100% of TB cases. However, that might not be, and usually is not, the best idea, because then you're going to be referring a huge number of people for diagnostic testing that don't actually have TB. So I think, like we saw in several examples today, it's all a balancing act between trying to maximize your sensitivity, but also reach a level of testing and a level of screening positivity and expert testing that you can handle in your screening program. So that's what I think the CAD calibration toolkit And the reactive adjustment method that Juno showed us can both allow you to do is to really fine tune your CAD threshold so that you are maximizing your sensitivity, but within parameters that you can work with in your screening. Thanks.
Thank you, Ceci. Muchas gracias. Sí, sí, sí. Sí, tengo a Leoni en lo que buscamos una pregunta de Brasil.
A question from Brazil, Leonie.
Gracias, Belkis. Buenos días,
Thank
buenas
you,
tardes con todos.
Leonid.
Bueno, quería aprovechar la pregunta, ¿no? Para un poco hacer un
Piggybacking on
resumen de
that
lo que ya han
question,
venido comentando, ¿no? La
and this is
estrategia
something
va a
that
depender de
has
muchas
been
variables, va a depender,
addressed. The strategy is
como
going
comentaba
to
Cecilia
come
también,
down to a number of variables.
de cuál es el grupo al que voy a intervenir, de la
The group
prevalencia de
I'm
la
going to
enfermedad en
be
este grupo.
working
Yo
with.
podría obviamente bajar el punto de corte para aumentar la sensibilidad, pero
You
tengo que
can raise
tener
the sensitivity
detrás
by lowering the
por qué lo
cutoff
voy a hacer,
point.
¿no? Mucho depende
But why would I
también
do
del
that?
siguiente paso, que es la capacidad
The
del
next
laboratorio.
step is
Comentaba en
the
las
lab's
presentaciones que
capacity.
yo
That's another
podría, si
factor.
tengo la capacidad de tamizar 100 personas
If I
y
can screen
obtener 30
100%
muestras diarias
and
y tengo la
cope with
capacidad de mi
30
laboratorio para tamizar,
samples
puedo
a
seguir
day,
adelante,
and I
pero
have that
va a
capacity
depender
to
de eso,
screen
va a
all of
depender
them,
de la disponibilidad
I'll
de
do
los
that.
cartuchos, disponibilidad de los equipos, ¿no?
But it's
De
going to
la
come down
logística
to
de las
the equipment, the
muestras.
logistics,
Hay una
the
serie de variables finalmente, y de
cartridges,
acuerdo a eso voy a
staff. And so there
decidir.
are a
Mi
number of factors
experiencia
that
al inicio de
play
CAD
into this.
nosotros empezamos
Our
usando el CAD
experience
4TV versión 6.0.
CAD with
Hicimos
CAD
un
4
análisis
to
de una muestra
4
inicial que
TB
tomamos.
version
Empezamos con un punto de
6.
50.
We started
Luego
with
empezamos a tener algunos desafíos, sobre
1.50. We
todo
had
porque
some
teníamos el
it was
28% de radiografías
50% cutoff, and
normales,
we had
lo que
some
significaba
challenges.
alrededor de
20% were
30 cuando hacíamos
abnormal
campañas de 100 casos,
X-rays.
100
This was
pacientes
100
por día, eran
screenings per
28, 30
day,
muestras por
28
día.
per,
Pero luego
samples per
tuvimos un
day.
segundo camión, ya
But
hablábamos de
then
casi 200 muestras al día. Ya
another
estábamos
truck
hablando de
was
60
bringing
muestras
200
entrando al
samples a
laboratorio.
day.
Tuvimos que
100
comprar
were
otra
sending
máquina
to
extra
the
y
lab. We had to buy
mejorar el
another
programa de
expert
laboratorio para
machine,
poder cumplir con
enhance or expand our
con
lab
toda la
so that we
demanda, ¿no?
could keep
Entonces
up
eso hay que
with that
tenerlo muy en
demand.
cuenta,
So we have to take that
y
into
uno
account.
puede más o menos ir afinando el punto de corte,
And you can
entendiendo que
fine
podría
tune the
perder
cutoff
algunos
point.
potenciales
I
casos,
understand
pero
that you
también
might
está
miss
el
some
ojo clínico, ¿no? En
cases,
algunas
potentially,
campañas agregamos un
subclinical
médico que
cases
está
in some
disponible que podría estar
campaigns.
mirando algunas de las radiografías o juntando la
I'm sorry,
clínica de
you
los
can have
pacientes, y a
a
pesar de que
doctor
tenga
looking at some of
una
those
radiografía
x-rays,
normal según el punto de corte que establecimos, podría indicar la colección también de una muestra de sputum. Cambio.
and also based on the cases that we have, you can look at the sputum.
Plan. Gracias, perdón, estaba hablando. Micrófono.
Thank
Perdón.
you,
Gracias, Leoni. Y es un
Leonid.
ejemplo de que corrobora lo que se ha mencionado
That
Juno,
corroborates
el tema de
what Juno
evaluaciones
was saying.
periódicas. Este punto de
The
corte
periodic
podría evaluación ajustar
reassessment
hasta
of the
encontrar
cutoff point and to fine tune it and adjust it until you find the optimum cutoff point
tamizaje sea más
to
eficiente.
ensure that our
Tenemos un
screening
par de
be the most
preguntas más.
efficient it can
Esta en
be.
este
We have
caso
a few
sería
more
para Juno,
questions.
que
This
sobre la
one is for
experiencia de
Juno
Manila.
about
Él
the
pregunta
experience
que
in
si el
Manila,
van
and they ask
tenía su
if
propio generador de
the
energía
van
eléctrica,
had its
acceso a
own
internet,
generator, access
porque
to the
Brasil está
internet,
queriendo tener una iniciativa similar a la de Manila.
because we would like to do something similar.
If the van had access to internet, was that the question again?
Yes.
No, actually. So we use the offline CAD for TB box. We didn't want to be reliant on the internet. Also, there were some issues with data protection. We wanted to maintain all the data on site. And so that's one of the reasons we use the offline box. But we did not have internet access in the van. Was the question related to using the cloud-based version of CAD for TB?
No, it's correct. Only del van, si el van tenía su propio generador de
Yes,
energía y
the question
acceso
was whether it
disponible
had
a
its
internet. El
own
van que
generator,
utilizaron en Manila.
the one used in Manila. Did it have a generator on board?
Ya
Is the other part of the question.
Okay, generator. Yes, it did have a generator. So there were two options in terms of power. We could plug into city power, which we did when that was available. But when it was not available, we could also use the generator in the X-ray. So we weren't completely reliant on city power. I did want to also add just to the last two comments about maximizing sensitivity, and both the speakers hit on some of the points. But one of the options that I gave for choosing the initial threshold is to set the threshold according to your testing capacity. And so that will be basically that will maximize your sensitivity. You can't go lower than that threshold because you won't have enough tests for referrals. So the idea of this reactive adjustment approach is that you can use that to set the initial threshold. So that's kind of your lower limit. Use the adjustment technique to slowly raise up your threshold if necessary, because the downside of using the testing capacity, you're going to be using more tests. And so that's going to increase costs. But at least it could be a starting point for you if you're really worried about sensitivity, and then slowly adjust as necessary, depending on what the data shows. So that would be one method to maximize sensitivity. Thanks.
Thank you, Junior. Y la última pregunta,
the last question
en relación a las herramientas de tamizajes que si se
regarding
podrían
screening
combinar, tanto la
tools.
evaluación clínica o evaluación médica,
Can you
la
combine
radiología
clinical
y
and
la
doctor
biología
evaluations,
molecular?
molecular
Si es
biology and
posible determinar
cardiology,
la sensibilidad y
or
especificidad
radiology
del
rather?
uso
Can you determine
combinado de estas tres
can you
herramientas de
combine
tamizaje.
these three
Para
tools to
Cecilia,
adjust the sensitivity?
Si es posible determinar
Is
la
it possible
sensibilidad y
to determine the
especificidad del uso de
sensitivity and
las tres
specificity
tecnologías
by making
de
use of
tamizaje
these
estudio un poco
three
en
screening
alumno,
methodologies,
la sensibilidad de cada una combinada?
combining the sensitivity of each one of the three
La
techniques?
sensibilidad combinada de la evaluación médica,
Doctor's
la
evaluation,
radiología y la biología molecular.
radiology, and molecular biology.
So the question is about, can we evaluate the sensitivity of a combined screening approach? And I think they mentioned 3 different methods. So yes, we can, and several studies have done this. I don't know of studies combining radiography and clinical evaluation with molecular testing was, I think, the third option. Since that is essentially the gold standard, that is that provides you with your answer. So typically symptoms and chest x-ray are often combined in a parallel approach. And for example, that's what's used in prevalence surveys. And so this is sort of what we think of as the most sensitive approach, because between those two, you will find the majority of cases. And we see from the data estimates that indeed that this parallel approach has the highest sensitivity, but it of course has lower specificity. Now, beyond that, combining 3 elements, perhaps not bacteriological testing, since we think of that as the gold standard, but combining other elements with those 2 types of approaches. I don't know of those yet. They may start to appear. I think it's an interesting area for research. For example, is there some way that you can combine some biomarkers with radiography and clinical evaluation to maximize, for example, is there a way to improve the specificity of screening while maintaining the high sensitivity with an approach like this? And we mentioned in the first session that CRP is a blood test that is approved currently only for screening people living with HIV, but this shows us that sometimes there are biomarkers that can give us some useful information. So I think this is an area of future research, but in general, parallel screening options, yes, are widely accepted and do maximize your sensitivity. However, they lower your specificity. So that's something to keep in mind.
Thank you. Muchísimas gracias, Cecily. Ya para cerrar esta sección de preguntas.
So thank you. Just to conclude this round of questions, I would ask our experts if you have any further comments you'd like to make.
Tu micrófono, Angélica.
¿Ahí me escuchan bien?
Sí, ahora sí, ahora sí.
Can you hear me okay? Yes.
Quería aclarar una consulta que están
I just have a question,
en donde preguntan por el
and
costo del
I
diagnóstico
see a question
con la
about the
herramienta,
cost
si es
of
que incluye el
diagnostic
costo
with the
de
tool, whether it
recursos
includes the
humanos,
cost of human
traslado. En este caso
resources
nosotros
and
utilizamos
transfer. In this
$9 y
case,
con
we're
eso lo que
using
incluye es el
$9,
flete del equipo
and
de
this
Gene Expert,
includes
el
freight for the
desabanaje y
Gene
el costo del
Expert
cartucho. Eso es lo que consideramos nosotros
piece of
para hacer
equipment and the cost
este
of
ejercicio.
cartridge. This is what
Pero
we consider for
podemos
this
hacerlo más
exercise,
adelante,
but we
ya
can do
incluyendo
it
todo
later
eso, para
on
ver también cuánto nos
and see
sale.
how much it would
Gracias.
be. Thank you.
Gracias, Angélica. Juno,
Thank you, Angelica. Juno,
¿algo comentar?
would you like to make any comments?
I'll just add that I'm very happy that all this discussion is going on. I think people are starting to realize, or have realized for a while, the importance of choosing the right threshold. I think maybe in the beginning when this technology came out, it seemed like people were just using 50 just because it was an easy number. And so people are realizing the complexities involved. I also am very happy to be part of this because I think having different options is great. Every project, every country is going to be different in terms of how they use CAD. And so depending on resources available and what the context is, I think having various options is going to be very helpful to implementers. But thank you for inviting me to this.
Thank you, Juno. Muy correcto, se tiene que adaptar a las
Thank you, Juno.
especificidades de cada país.
Yes, we
Esta
will
es la
have
ocasión de
to
usar herramientas
adjust to the
normales. Muchísimas gracias, Juno.
specificities
Cecilia,
within the countries. Thank you,
¿algún
Juno.
comentario
Cecily,
adicional?
any additional comments?
Yes, I just wanted again to, like Juno, applaud the session, and it's very good discussion underway, and I think it's a really great opportunity. I also wanted to echo his comments about the, I think it's good that we have some choice in the approach to calibrate CAD. I think we've talked about this, Juno and myself, a lot in the past several months, and that this is an area that's very important. We want people to think about setting the CAD threshold, but we don't want it to be too complicated or too overwhelming that that people sort of forget about it and just go with you know, the sort of preset threshold or use something that's not appropriate. So there are different approaches depending on what types of data you might have at hand, what your capacity is. And I think so we presented something that we think gives you a really good scientific picture of how the CAD is operating. If that's not available, though, I think the approach that Juno presented is a really good alternative and a really good method to quickly understand how the CAD is operating in your local setting with just measuring, you know, minimal pieces of data and being able to quickly make changes that can be really impactful to your screening program. So I hope people see that there are options and that it's not overwhelming, and that you can always reach out to the colleagues who are on this call if you need help with it. But I'm really happy people are paying attention to this topic. Thank you.
Muchas gracias. Gracias.
Thank you very much.
Sí, sí, las presentaciones de este webinar y de los
The
anteriores
presentations
están
for
disponibles en el
this
enlace que
webinar and the previous
en
ones
el
are
chat de
available
Zoom,
in
pero
the
también van a poder tener acceso en cada uno de los enlaces que están en nuestra
link that
página
we
web. Cada
submitted,
webinar tiene un
but
enlace.
each
Ustedes pueden
webinar
acceder al
has a
video, la
link, and there you
grabación del
can see
video, y
the
van a
video
ver también
recording,
más
and you
información en
will
los
also
enlaces.
see further
Muchísimas
information later on.
gracias. Yo le paso la
Thank you very
palabra
much.
a
And I
Pedro,
give the
que
floor
cierra.
to Pedro,
Muchísimas gracias a todos los
who will be
participantes
closing, and I thank all of the
que estuvieron.
participants
Gracias.
who were here with us. Thank you.
Muchas gracias, Belkis.
Thank you,
Buenos días, buenas
Welkis,
tardes,
and good
colegas. Les
morning,
saluda
good
Pedro Abadilla,
afternoon,
asesor
colleagues.
regional
This is
de
Pedro
tuberculosis
Abedilla,
aquí en el equipo regional
here with the regional team in Washington. First, I would like to thank all the excellent panelists that we had, Dr. Pedro Jimenez with the radiology department here in Washington, Jesus Sanders, Cecily from WHO, Juno from Doctors Without Borders, and Angelica Melina with the National TB Program of Paraguay. Excellent presentations. Thank you all for being here with us, sharing all of your experiences that we know will be very useful for the countries of the region. Again, as Cecily Juno mentioned, there is growing interest in this topic. We have had more than 300 participants in this webinar, and we have had similar numbers in the past or even higher. And I would like to thank our interpreters and also Pajo's team. Francisco, we thank you for the organization. And as we mentioned before, we're going to share the recordings and also the presentations, and we have them translated into English and Spanish. Welkis has shared the link in the web, but we're also emailing this, and we are gathering, collecting all of this information so that it is available and so that you can easily have access to it. And we will be communicating the dates for the upcoming seminars in a short period of time, and this has to do with also active case findings for TB. And as Ernesto Belkis just mentioned, and as Cecily mentioned, from PAHO, we are completely available to continue to support you on what we saw today, radiation safety, local regulations for the use and implementation of the X-ray equipment and screening campaigns, and also for the selection of threshold points, which we know is a key topic. We have seen two tools or methodologies we can use, PDR, as well as the reagent method we saw with Juno, and we are here available within PAHO to continue to support the countries. And one of the very important aspects to bear in mind from the countries and the TB program as part of those implementation programs and active search, active findings using these technologies. We will continue, as I mentioned before, with the webinars on this topic and also on preventive care. The idea is to continue to share recommendations, but also some practical examples as to how we can solve and clear any doubts and make progress. With this, I thank you. I would like to thank the panel members, the participants who shared questions and comments. Have a nice day, and we will continue.